Hi everyone, and welcome to The Sleepy Scientist. I'm really happy you're here. Tonight, we're going to go on a calm and quiet trip to learn something amazing. So get comfy, take a deep breath, and let's enjoy this peaceful science story together. Before we start, tell me in the comments, where are you watching from and what time is it for you right now? If you like relaxing science videos, don't forget to tap the like button. Now let's begin.
Imagine drifting through the quiet dark of the universe, where stars whisper their last words in gentle light and time itself seems to exhale slowly. In this silence, there is a place where even light loses its will to travel onward. Here lies the event horizon, the soft edge of a black hole, a boundary not of walls or fences but of surrender. It is not a hungry monster in the way that stories frighten us. Rather, it is a patient, unhurried collector of what chooses to wander too close. Picture it like a pond at night, so still you can see stars reflected in its depths. A black hole's gravity curves space in much the same way, like an endless pool whose surface bends and bends until it folds in upon itself. Anything that touches this quiet edge disappears from sight, as though it were sinking below the surface of a dream. But it does not do so in violence. It is more like the hush that follows a lullaby, a silence that holds everything close. The event horizon is defined not by what it does, but by what it allows. It is the last invitation. Once you cross it, all paths point inward. Light itself curves and curves until it cannot leave. Time stretches, slows, and stops altogether at the edge for an outside observer. If you watched someone fall in, they would seem to slow forever, their last image hovering on the edge like a fading memory. It is the universe's way of telling us there are places where our rules must yield. Black holes are born not of chaos but of collapse. When a massive star burns through its fuel, there is a moment when its core can no longer hold back the crush of gravity. The star's outer layers may explode in a supernova painting space with brilliant light, but the core folds in upon itself endlessly. Gravity wins. It is the simplest story told in the softest way. Even the strongest lights can be calmed by gravity's patient embrace. Some black holes are only a few times heavier than our sun. Others, called supermassive black holes, are millions or billions of solar masses. These giants rest at the centers of galaxies, including our own. There, in the quiet heart of the Milky Way, sits Sagittarius A*, a supermassive black hole that holds our galaxy in its gentle grip. Stars swirl around it in graceful orbits like dancers who know not to approach too close. The black hole does not chase them. It waits. It is content. Scientists have learned to see black holes not directly, but through their influence. We watch the dance of nearby stars, the swirl of hot gas spiraling in. As matter nears the event horizon, it heats up, glowing in X-rays and light we can detect. It is a paradox. Black holes are the darkest places in the universe, yet the space around them can blaze with light. It is like seeing the glow of a candle just before it is snuffed out forever. Imagine floating near one, not being pulled in but merely observing. You'd see space bend in strange ways. Background stars would appear distorted, their light curving around the black hole like river water flowing past a stone. This bending is called gravitational lensing. It lets us see rings of light, called Einstein rings, where light from distant galaxies wraps around the black hole's gravity well. It is a natural lens, gentle in its manipulation of the universe's light. Einstein's theory of general relativity first told us that mass curves spacetime. Black holes are the ultimate expression of this idea. They are not objects in space, so much as holes in its very fabric. Think of them as valleys so deep no traveler can climb out. The event horizon is the lip of the valley, the point of no return. Yet the shape of that valley reaches outward, tugging gently on anything that nears. Some people picture black holes as cosmic vacuum cleaners, devouring everything in their path. But space is vast and empty. A black hole only influences what comes too close. Most of the time, it waits in silence. A star might wander too near, pulled apart in a slow tidal dance, its gas spiraling in to feed the black hole's glow. But these events are rare and spectacular, the quiet punctuated by brief bursts of radiance. Inside the event horizon, our physics breaks down. We cannot see what happens there. Equations hint at a singularity, a point of infinite density where time and space lose meaning. But these are our words for our ignorance, our humble admission that we do not know. Some theories suggest the singularity may not be a point at all, but a region where quantum effects become important, smoothing out the infinities. It is a question we ask softly, knowing the universe holds its secrets close. The idea of falling in is a slow one. For the falling traveler, time moves normally and they would cross the event horizon without noticing anything special. But to a distant observer, their fall seems to freeze at the edge forever, red-shifting, fading into darkness. It is a beautiful contradiction. For one, the journey ends. For the other, it never finishes. Both are true in their own way. Black holes remind us that time is not absolute. It stretches, twists, and folds in their presence. Clocks run slower near them. Light loses energy trying to escape, shifting red. These effects are not science fiction but are measured and real. Our satellites use corrections for these relativistic effects to keep GPS working. The universe is a patient teacher, offering gentle lessons even in the technology we use daily. Now imagine a black hole wandering the galaxy like a quiet pilgrim. Such objects exist, rogue black holes moving silently through space. They are invisible unless they pass near something to betray their presence. We suspect there are many in our galaxy, quiet and undetected, peaceful in their solitude. They are not threats, merely wanderers. Even supermassive black holes grow slowly, through the gentle accretion of gas or by merging with others. When galaxies collide, their central black holes may dance around each other in vast, slow orbits before finally merging in a cataclysm of gravitational waves. But even these waves, once unleashed, travel the universe like ripples on a calm pond, spreading the story of the merger to distant corners of space. We can detect these ripples now, using instruments like LIGO and Virgo, listening for the quiet symphony of gravity itself. There is something calming about knowing the universe contains such extremes. Black holes are limits. They tell us there are places beyond which we cannot know, cannot see, but they do not threaten us. They are peaceful in their inevitability, patient in their waiting. In this way, they are like sleep itself, drawing all that comes near into rest. And so the event horizon is not a maw but a cradle. It holds what falls to it, wraps it in darkness, and removes it from our sight. It is the edge of knowing, the place where questions become softer. We do not need to fear it. We can simply wonder. We can imagine its presence at the center of our galaxy, holding us all in its quiet gravity, a gentle anchor in the vast sea of stars. Let yourself drift with this thought, that even in the deepest darkness there is order, that even gravity's strongest pull is just nature doing what it does, calmly, patiently, forever. The universe is not rushing. It is not angry. It is simply there, waiting, breathing, holding everything in place. And the event horizon is its quietest promise that some things will remain mysteries, safe in the dark. Let's drift deeper now, into the quiet truth of what black holes teach us about space and time. When we speak of an event horizon, we are really speaking of a surface with no substance, no matter to touch or hold. It is not a wall but a threshold, a mathematical boundary that defines what cannot escape. Scientists explain it like a sphere drawn in space, marking the distance from the center at which the pull of gravity becomes absolute. Nothing, not light, not sound, not even our most stubborn questions, can cross back once it has passed this gentle perimeter. Yet from far away, black holes reveal themselves in subtle ways. Their gravity shapes the orbits of nearby stars with slow, graceful precision. Astronomers patiently map these motions over years and decades, learning the mass and presence of something they cannot see. It is a science of inference, of reading the invisible through what is visible. Much like watching reeds bend and knowing the wind, we see stars curve and know a black hole is there. This quiet evidence led to the discovery of the supermassive black hole in our own galaxy. At the center of the Milky Way, Sagittarius A sits in patient darkness. It is roughly 4 million times the mass of our Sun, yet it occupies a space no larger than our solar system. Around it, stars swing in tight, quick orbits, the way bees circle a hive. These stars are our witnesses, testifying in silent curves to the immense gravity that holds them. Scientists have observed this motion with immense care. Using instruments like the Very Large Telescope and the Keck Observatory, they tracked individual stars for decades. One, called S2, makes an elliptical orbit around Sagittarius A every 16 years. When it swings close, it speeds to thousands of kilometers per second, then drifts slowly away again. It is like a heartbeat measured in decades, slow and steady, reminding us of time's patient scale. And black holes shape more than stellar orbits. They influence entire galaxies. The biggest black holes are found in the cores of massive galaxies, where they seem to play a quiet role in regulating growth. When matter spirals into them, it heats up and can blast out jets of particles and radiation that reach far into space. These jets can slow star formation in surrounding clouds, a kind of cosmic gardening where black holes help prune and shape their environment. It is an odd idea. Something that devours also nourishes by limiting, a caretaker that works by removing. But these flows of energy are not chaotic explosions. They are steady, collimated beams that can stretch for thousands of light years, shining in radio waves and X-rays. Imagine a lighthouse on a dark sea, turning slowly, sending its light across the black canvas. These jets are signs of a black hole's feeding, but also of its influence, helping maintain balance in its cosmic neighborhood. This balance is not forced. Space is mostly empty after all. Black holes cannot hunt or chase. Their influence is passive, requiring matter to come near on its own. When galaxies merge, their central black holes may eventually meet and combine, but they do so only after long, slow dances. Their gravitational fields weave together like threads, pulling their galaxies into new shapes. This process can take hundreds of millions of years, a time span beyond any human urgency. Gravitational waves offer us another window into this gentle drama. When black holes merge, they send ripples through spacetime itself. These waves are incredibly faint by the time they reach Earth, like the quietest of whispers across the cosmos. Yet our detectors are sensitive enough to hear them. LIGO and Virgo have recorded these soft signatures, helping us confirm that black holes not only exist but move, combine, and sing in gravity's language. This has changed how we think of space. No longer is it an empty stage for matter to move upon. Instead, space itself can ripple and curve. Gravity is not a force in the old sense, but the bending of spacetime around mass. When two black holes merge, they warp space like stones dropped into a pond, sending ripples in all directions. These ripples travel unimpeded, crossing billions of light years to reach us, carrying news of ancient unions. Yet even in this dynamic, the universe remains slow. These waves travel at light speed but emerge from events that unfold over vast ages. The merger itself is quick, but the approach takes eons. It is the ultimate slow dance, two massive objects locked in orbits that decay gently over millions of years until they finally kiss and combine. There is no violence from their perspective, just the patient pull of gravity doing what it always does. In their cores, black holes remain unknowable. Our equations fail at the singularity. Time and space themselves seem to end or at least become something we cannot describe. This is not a failure of the universe but of our language. We are used to measuring, predicting, explaining. But here, at the heart of gravity's well, there is only humility. We can say the singularity exists, but not what it is. The event horizon protects this mystery perfectly, hiding it forever. This is part of why black holes are peaceful teachers. They show us limits. We learn that knowledge has edges, that curiosity must sometimes rest. When you think of a black hole, think of it not as a devourer but as a librarian that closes the final book. The information may be there still somewhere, but the covers are shut. We do not have the key. Some scientists wonder if information is lost or preserved, scrambled on the event horizon or woven into Hawking radiation as it evaporates. These debates are whispered questions in the dark. Speaking of Hawking radiation, even black holes are not truly eternal. Over unimaginable timescales, they may lose mass slowly, shedding energy in tiny, cold trickles. For the biggest black holes, this process is so slow it would take longer than the age of the universe to notice. But it reminds us that nothing lasts forever. Even these sleeping giants have lifespans, measured in trillions of years, patient beyond imagination. Picture that, a black hole slowly fatting, its event horizon shrinking, the boundary dissolving until it is gone. No explosion, no collapse, just a slow unwinding like a candle that burns until the last drop of wax melts. The universe itself will have changed by then, galaxies dispersed, stars dead, space cold and quiet. The black hole will simply be gone, its presence erased, leaving only the memory of its pull in the history of spacetime. In this way, black holes are gentle endings. They mark the last pages of many stories, of stars that died, of gas that fell in, of light that tried to flee. They hold these things, contain them, make them part of something larger, and even as they vanish, they release a tiny bit of that history back to the universe, like old tales whispered to an empty room. So when you close your eyes and imagine the event horizon, do not see a trap or a monster. See a horizon at dawn, the line where light fades gently into night. See it as a promise that there will always be mysteries, that some things are allowed to rest in silence. The universe is patient, and its quiet places are not empty but full of meaning. Black holes remind us to be humble before what we do not know, and to let that humility soothe us. They are the universe's slow breath, in and out over billions of years, a testament to the calm inevitability of gravity, a reminder that everything changes but nothing is rushed, that even in collapse there can be order, that even the strongest pull can be quiet. Let these thoughts settle over you like nightfall, gentle and unhurried, a calm truth in a restless world. Now let us rest within the quietest part of the story, at the edge where knowledge becomes wonder. The event horizon is not only a scientific concept, but a gentle metaphor for all the places where certainty fades into mystery. Here, even time seems to loosen its grip. For an outside observer, anything falling toward the event horizon appears to slow, its final moment stretched into eternity. It is not destruction, but a soft, endless farewell, like watching the last glow of sunset linger long after the sun itself has dropped below the horizon. Within this silence lies a lesson about perspective. For the falling traveler, nothing strange happens at the horizon. They cross it in an instant, unaware of the boundary's significance. Time moves as usual, and they continue their journey inward without pause. This contradiction, frozen to one observer, smooth to another, is not a trick but a truth of spacetime. It reminds us that our view is never the whole view, that even in the physical universe, different vantage points reveal different realities. Black holes are boundaries of knowledge as well as matter. We cannot see past the event horizon. Even our most advanced instruments can only map its edge. What lies inside remains hidden, not by choice, but by the very structure of the universe. The equations that predict singularities tell us more about the limits of our understanding than about what is actually there. We know that gravity becomes immensely strong, that spacetime curves towards something we cannot describe. But what it truly is, whether a point of infinite density or something gentler, smoothed by quantum rules, we do not know, and perhaps that is fitting. Some physicists imagine that black holes could be windows to other universes, bridges through spacetime called wormholes. Others say this is unlikely, that any such tunnel would pinch shut too quickly for anything to cross. These ideas are not settled. They remain questions, dreams, hopes whispered between lines of mathematics, but they speak to our unending curiosity. Even when faced with something that seems to forbid knowing, we find ways to ask. In the last decades, our ability to study black holes has grown in unexpected ways. The Event Horizon Telescope captured the shadow of a black hole in the galaxy M87, showing the world the dark circle surrounded by a ring of light. That light comes from heated gas spiraling in, compressed and glowing before it crosses the threshold. We cannot see the black hole itself, but we can see the silhouette it casts against the radiance of falling matter. It is like watching the dark pupil of an eye framed by fire. This image was not just a photograph, but a triumph of collaboration. Telescopes across the globe worked in unison, synchronizing their views to create a virtual dish the size of the Earth itself. Scientists in different countries, speaking many languages, shared data and ideas. The result was a single image that spoke to everyone in the same tongue. This is what the edge of knowing looks like. Even here, at the quiet limit of light, human cooperation shone. These advances did not make black holes less mysterious. They made them more real. No longer abstract equations alone, they became part of our shared vision of the cosmos. We could see their influence, measure their mass, even hear the ripples from their mergers. Gravitational waves, faint and patient, arrived at our detectors after journeys of billions of years. These ripples confirmed what Einstein imagined and showed us that space itself can carry the memory of violent unions in the gentlest of ways. Even Hawking radiation, the idea that black holes slowly evaporate, is not a violent process. It is cold, slow, inevitable. Virtual particles near the event horizon can separate, with one falling in and the other escaping, carrying away a tiny bit of mass. Over time, this process empties the black hole of its energy. For small black holes, this would happen quickly, but for giants like Sagittarius A, it would take a span longer than the age of the universe to even begin to notice. It is like watching a mountain erode grain by grain over eons. This slow unwinding adds to the peaceful image. Black holes do not roar as they die, they fade. Their horizons shrink, their secrets slipping away in soft, almost imperceptible drips of radiation. In the end, even they must surrender to time, releasing everything they held so tightly. It is not punishment, merely the law of change. Nothing remains forever unchanged, not stars, not galaxies, not even these sleeping giants. Our study of black holes is also a study of humility. We must admit what we cannot see, cannot test, cannot know. Yet even in that humility lies beauty. To recognize limits is not defeat but wisdom. The event horizon teaches us that the universe has places where questions must soften into wonder. It asks us to respect mysteries, to sit quietly before them without demanding they yield their answers. And perhaps this is why black holes feel comforting despite their reputation. They are not threats in our lives. Even the supermassive one at our galaxy's center is so far away that it poses no danger. Instead, it holds the Milky Way together, anchoring the stars in their slow spiral. It is a presence that is steady, reliable, patient. In a universe that changes, it offers a kind of cosmic constancy. When we look up at the night sky, we see only the surface of things. Stars sparkle, planets wander, nebulae glow. But hidden among these lights are the black holes, silent, invisible yet fundamental. They are part of the architecture of galaxies, the keepers of their mass and motion. Their gravity shapes paths over millions of years. They are the punctuation marks in the story of the cosmos, full stops where one chapter ends and another begins. There is something tender in this idea. Black holes do not destroy meaning, they complete it. They offer rest to the matter that falls in, giving it a place to end. They preserve information in ways we do not yet understand, perhaps forever. Even as they evaporate, they may carry that information outward in delicate radiation. Nothing truly disappears, only transforms in ways beyond our sight. Imagine floating far from Earth, watching a black hole from a safe distance. You see the swirl of gas, the distortion of starlight, the quiet ring of its shadow. It does not move toward you. It does not call. It simply exists, serene and unbothered, patient as time itself. You feel small but not afraid. You understand that the universe is vast, old, and full of secrets that do not threaten you but invite you to wonder. Let these thoughts stay with you like a lullaby. The universe is not in a hurry. Black holes are its sleeping giants, resting at the centers of galaxies or wandering alone through silent space. They are reminders that even in collapse there can be calm, that even in endings there can be peace. When you think of them, think of patience, of slow change, of the quiet promise that some mysteries are meant to remain. And as you drift into sleep, let the image of the event horizon be not a boundary of fear but of rest. A gentle edge where light itself surrenders, where time pauses, where questions give way to silence. The universe holds these places for us, inviting us to close our eyes and trust that even in the deepest darkness, there is order, there is meaning, there is peace. Imagine space itself as something more than emptiness, something that can breathe, flex, and move in its own quiet rhythm. When we think of space, we often picture a vast black canvas sprinkled with stars, a vacuum so empty it seems lifeless. But this emptiness is deceptive. Space is a fabric that can bend and stretch, a living stage on which galaxies and stars perform their slow dances. This idea is at the heart of modern physics, and it reveals the universe to be far softer and more patient than we ever imagined. Long before scientists could prove it, some suspected that gravity was not just a force acting at a distance, but something woven into the very nature of space itself. Isaac Newton described gravity as an invisible pull between objects, but he could not say how it worked. It was like a promise. Things fall toward each other, but the why remained silent. Centuries later, Albert Einstein offered an answer with his theory of general relativity. He said that mass and energy tell space how to curve, and curved space tells objects how to move. Gravity, in this view, is not a force in the usual sense, but the shape of the universe itself. To imagine this, think of a stretched sheet held tight at its corners. If you place a heavy ball in the center, the sheet dips around it. Now, if you roll a smaller ball nearby, it curves toward the heavy one, following the slope. This is the classic analogy for how the sun holds the Earth in orbit, not by pulling it invisibly, but by bending the space around it. The Earth is simply following the straightest path in this curved space, a path called a geodesic. It is a soft, inevitable motion, like water flowing downhill. But space is not a flat sheet in reality. It is a four-dimensional fabric that includes time. When mass bends space, it also bends time. This is why clocks run slower near massive objects, a fact measured with precision on Earth. Satellites in orbit must adjust for this time dilation to keep GPS systems accurate. Even here in our daily technology, we see the slow breath of spacetime at work, a gentle shift that would go unnoticed without careful attention. This bending and flexing of space becomes most dramatic near massive objects like stars and, especially, black holes. Near a black hole, spacetime curves so intensely that all paths point inward. Light itself follows these curves, trying to escape but eventually surrendering to the slope. Time slows near the event horizon, freezing from the perspective of an outside observer. It is as though the universe itself inhales deeply, holding its breath forever at the edge. Yet spacetime is not rigid. It is dynamic. When massive objects move, they create ripples in this fabric, gravitational waves. These waves travel at the speed of light, spreading out through the cosmos like the ripples on a pond after a stone drops in. But these cosmic ripples are incredibly faint. Even when cataclysmic events like black hole mergers occur, the gravitational waves they produce are so subtle that they shift the distance between objects by less than the width of an atom across kilometers. Detecting them required patience, precision, and faith in the universe's gentle signals. When scientists first detected gravitational waves in 2015, it was like hearing the universe whisper. Two black holes, each many times the mass of the Sun, had spiraled together in a distant galaxy over millions of years. Their final embrace sent ripples through spacetime that traveled over 1 billion light-years before softly brushing past Earth. The instruments of LIGO, laser interferometers capable of measuring distances unimaginably small, captured these ripples. It was proof not only of black holes colliding, but of the very pliability of space itself. Imagine those waves traveling across the universe, undisturbed by matter, never weakening except through expansion. They carry the memory of that merger in their form, a quiet record of an ancient event. Like sound in air, these waves encode the story of their source. By studying them, scientists can learn about the masses, spins, and distances of the black holes involved. Each detection is like receiving a letter written in the alphabet of gravity. But the breadth of spacetime is not limited to violent events. Even in the calmest corners of the universe, space expands. Since the Big Bang, space itself has been growing, carrying galaxies with it like raisins in rising bread. This expansion is not an explosion in space, but an expansion of space itself. Galaxies do not fly through a pre-existing void. Rather, the void itself stretches. Light traveling through this expanding universe is stretched too, turning from blue to red over cosmic distances, a gentle aging that records the universe's history. This redshift tells us not only that the universe is expanding but how quickly. By measuring it, astronomers discovered that the expansion is accelerating, driven by something we call dark energy. This term is a placeholder for our ignorance. We do not know what dark energy is, only that it makes up about 70% of the universe and acts with a quiet, persistent push. Unlike gravity, which pulls matter together, dark energy gently drives everything apart, a slow exhale that will continue for billions of years. In this context, black holes seem like the opposite of expansion. They are regions where gravity has won completely, pulling matter into the smallest possible space. Yet both phenomena, cosmic expansion and gravitational collapse, are expressions of spacetime's flexibility. The universe can stretch and it can pinch shut. It is not a contradiction but a balance, the full range of what space and time can do. Consider the vast scale of this breath. When we breathe, it is a matter of seconds. When the universe breathes, it takes billions of years. The first atoms formed when space was only a few minutes old. Stars and galaxies emerged hundreds of millions of years later. Today, 13.8 billion years since the Big Bang, the universe is still growing, its breath long and slow. Black holes, formed from dying stars or the mergers of galaxies, mark the places where this breath turns inward, where the expansion is locally overcome by gravity's calm pull. But even black holes cannot halt the expansion of space between galaxies. They anchor the structures within galaxies, holding stars in their slow orbits, but they drift apart with the cosmic flow. The space between galaxies grows ever wider. In the far future, distant galaxies will slip beyond our view, their light stretched so much that it fades into darkness. The universe will become a quieter, lonelier place. Yet even then, black holes will remain, patient and enduring, holding their own domains in a cosmos growing colder and dimmer. This is the slow breath of spacetime, expansion and contraction, movement and stillness, all proceeding without hurry. It is a reminder that the universe is not rushing. Galaxies collide over hundreds of millions of years. Black holes merge over billions. Even the evaporation of black holes through Hawking radiation will take trillions upon trillions of years. The universe keeps time on a scale beyond our comprehension, but not beyond our imagination. When you lie back and look at the stars, you see the light of ancient suns, stretched by the expanding universe, curved by the gravity of intervening objects. Every photon carries a story of spacetime's gentle shapes, and in those shapes is the memory of everything that ever was. The formation of atoms, the birth of stars, the merging of black holes, the slow drift of galaxies. All of it written in the language of curved space and stretched time. Let this thought settle softly, that the universe is not a void but a living fabric, capable of bending and rippling, of growing and pulling in. It breathes, slowly and silently, in ways that reveal themselves only to the most patient of observers. And in its breath lies the story of everything that has ever existed, told not in words but in curves, ripples, and the gentle glow of ancient light. Let's move deeper into the slow breath of spacetime and see how this gentle, cosmic rhythm affects the lives of stars and galaxies, how it sculpts the universe without haste or force. When we speak of spacetime bending, we do not mean it cracks or breaks. It curves smoothly, elegantly, as though it were a silk sheet laid over invisible forms. This curvature guides the paths of planets, the swings of stars around galactic centers, and even the flow of entire clusters of galaxies drifting through the expanding universe. It is a design without a designer, a rule that emerges naturally from mass and energy themselves. Think of our own solar system. The sun bends space around it so that Earth follows a curved path we call an orbit. But this orbit is not a circle drawn by hand. It is the straightest path possible in the sun's curved spacetime. Earth moves not because it is pulled along a string, but because spacetime itself says this is the way to go. In this sense, gravity is not an external force acting upon Earth but the very shape of its world. This is true everywhere in the universe. The same gentle guidance applies to the moons around planets, the stars within galaxies, the galaxies themselves as they form vast webs and filaments stretching for hundreds of millions of light years. This cosmic web is another expression of the universe's slow breath. Matter is not evenly spread out but forms a lacework of clusters and voids. Gravity draws matter together over billions of years, forming strands of galaxies connected like dew on a spider's web. Between these strands lie enormous voids, expanses so empty they dwarf even our largest galaxies. The process that created this structure was not rushed. It began with tiny ripples in the density of the early universe, amplified over eons by gravity's patient pull. The result is a pattern both complex and calm, a frozen record of the universe's early fluctuations. We can see evidence of this structure in the cosmic microwave background, the faint afterglow of the Big Bang. When we study this light, we see tiny variations in temperature, small differences that seeded the vast structures we observe today. This background is a fossil of the universe's infancy, stretched across the sky. It is like a baby picture of everything, showing the early breath of spacetime before it grew into the adult complexity of galaxies and black holes. As we zoom in from these grand scales to individual galaxies, we see the same principles at work. Galaxies are not static objects. They are islands of stars, gas, dust, and dark matter bound together by gravity, rotating slowly over billions of years. Spiral galaxies like our own Milky Way are shaped by this rotation, their arms winding gently like cream stirred into coffee. These arms are not solid structures but waves of density moving through the galaxy, guiding the formation of new stars in their wake. Everything about them speaks of patience. Stars are born, live for millions or billions of years, and die, enriching the galaxy with new elements in a slow cycle of creation and destruction. At the centers of many galaxies lie supermassive black holes, quiet anchors holding the swirling stars in place. These black holes grow slowly, consuming gas and merging with other black holes when galaxies collide. Their feeding is not constant but episodic, with long periods of quiet interrupted by bursts of activity as matter spirals inward, heating up and shining brightly before crossing the event horizon. These feeding episodes can create jets that extend thousands of light years, shaping the surrounding galaxy and even influencing star formation in neighboring regions. The black hole is both a consumer and a gardener, tending its galactic home through gravity's subtle influence. Even as galaxies merge, a process that can take hundreds of millions of years, the underlying rules remain gentle. Two galaxies approaching each other do not crash like cars on a road. Their stars are so far apart that direct collisions are rare. Instead, gravity choreographs a slow dance, their shapes distorting and mixing as tidal forces pull at them. Over time, they may settle into a new, larger galaxy, their central black holes orbiting each other before eventually merging themselves. This final union sends gravitational waves rippling across spacetime, a quiet announcement of change to the universe. These gravitational waves are another testament to spacetime's pliability. When black holes merge, they do not simply disappear. Their mass and spin combine, and the resulting black hole settles into a new, stable shape by shedding excess energy as gravitational waves. These waves carry away the memory of the merger in their gentle vibrations, traveling outward forever unless absorbed by something along the way. Our detectors on Earth are sensitive enough to pick up these tiny distortions, allowing us to listen to the universe's slow breath, one merger at a time. Beyond individual events, the entire cosmos is expanding. This expansion is not a force pushing galaxies apart but a property of spacetime itself. The distance between galaxies grows because the fabric of the universe is stretching. Galaxies are not moving through space away from each other so much as space itself is increasing between them. This distinction is subtle but important. It means that on the largest scales, there is no center to the universe's expansion, no privileged point. Every observer sees other galaxies receding, a universal truth woven into the fabric of spacetime. The rate of this expansion is not constant. For billions of years, gravity worked to slow it down, pulling matter together. But in the last few billion years, something has reversed this trend. Dark energy, a mysterious property of space itself, is causing the expansion to accelerate. This acceleration is gentle but persistent, a cosmic exhale that will continue indefinitely if our understanding is correct. We do not know what dark energy is, only that it exists and shapes the fate of the universe. Its presence is another sign that spacetime is not static but dynamic, capable of behaviors we are only beginning to understand. Black holes stand in contrast to this expansion, marking the places where gravity remains dominant. Within galaxies, they keep stars in ordered orbits, resisting the pull of cosmic expansion locally. They are pockets of collapse within an expanding universe, quiet witnesses to both contraction and growth. Their very existence shows that spacetime can do more than stretch. It can pinch shut, fold in on itself, create regions cut off from the rest of the cosmos. These regions are not violations of cosmic rules, but expressions of them, proofs of how spacetime's flexibility can lead to both vast openness and perfect closure. And yet, for all this complexity, the universe remains calm. Its grandest changes unfold over spans so long they escape ordinary human reckoning. Stars live and die over millions or billions of years. Galaxies evolve over hundreds of millions. Black holes merge over billions. Even the evaporation of black holes through Hawking radiation will take timescales that dwarf the current age of the universe. Nothing is rushed. The universe has all the time it needs, and it uses that time with a patience we can only admire. When we study spacetime's slow breath, we are invited to slow our own thoughts, to see our brief lives in context. The worries and urgencies of daily life are tiny ripples on a vast sea. By looking outward, we can learn to breathe more deeply ourselves, to take comfort in the universe's unhurried pace. It is a reminder that change need not be forced or violent, that growth can be slow and steady, that even the most dramatic transformations, like the formation of black holes, are part of a natural, inevitable flow. As you let this vision sink in, imagine the universe breathing in and out over eons, galaxies drifting apart, black holes forming and merging, gravitational waves rippling through space, all part of an unbroken, gentle rhythm. It is not chaos but quiet order, not emptiness but subtle structure. In this cosmic breath, everything finds its place, and even the deepest darkness holds meaning. Now let us drift toward the gentle closure of this story, exploring how the slow breath of spacetime reveals the deepest truths about our universe and our place within it. Imagine looking out at the night sky, the vast spread of stars and nebulae, knowing that every point of light sits within a space that is not static but alive. Space is not an empty container but a participant in every cosmic event, curving around mass, carrying light, stretching between galaxies. Even when it appears silent, it is full of subtle motion and memory, holding the record of all that has happened since the beginning of time. The idea that space itself expands is perhaps the most humbling lesson modern science has given us. In the early universe, matter and energy were packed together in a dense, hot state. As time passed, space itself stretched, cooling and thinning, allowing the first atoms to form, then stars, then galaxies. This process did not occur in an existing void. It created the void as it went. There was no outside into which the universe expanded. The expansion was of space itself. Every point receded from every other, not because it was pushed, but because the distance between them grew. It is a soft, persistent process, one that continues today. We know this because of the redshift of light. As space expands, it stretches the light traveling through it, shifting it toward longer, redder wavelengths. When we look at distant galaxies, we see them as they were millions or billions of years ago, their light softened and aged by the universe's growth. This cosmic redshift is like the slowing of a song played on a tape that stretches over time, a gentle, measurable record of expansion that scientists use to chart the universe's history. This expansion, however, is not uniform in its effects. Within galaxies, gravity remains strong enough to hold stars together, keeping them in slow orbits around the galactic center. Black holes, especially supermassive ones, deepen this stability. They are like anchors in a river that continues to widen, holding the local current steady even as the banks drift farther apart. In this way, the universe can expand as a whole while maintaining pockets of calm, ordered structure. Galaxies become islands in an ever-widening sea, each one with its own history, its own quiet story shaped by gravity's patient guidance. At even larger scales, the universe is structured in filaments and voids. These structures are not imposed but arise naturally from tiny variations in the early universe's density, amplified by gravity over billions of years. The cosmic web is a frozen record of these gentle differences, a memory of the universe's earliest breath. Observing this web teaches us about the balance between gravity and expansion, the way space bends to gather matter even as it grows overall. It is a dance that has no choreographer, but is nonetheless beautiful in its outcome. Black holes stand as the most extreme participants in this dance, where gravity wins completely, space-time curves so steeply that no path leads outward. But even these dark regions are shaped by the larger environment. Black holes grow by feeding on gas and merging with others, processes governed by the surrounding galaxy's structure and the broader cosmic flows. They are not isolated monsters but parts of a connected whole. Their formation, evolution, and eventual evaporation are all part of spacetime's slow, universal breath. Consider the end stages of black holes. Over unimaginable timescales, they emit Hawking radiation, losing mass particle by particle. For stellar mass black holes, this evaporation is effectively unnoticeable over the current age of the universe. But in theory, given enough time, they will fade away completely, returning their energy to the universe in the most patient way possible. There is no drama in this process, only inevitability, a slow release, like the last warmth leaving a cooling ember. Even in their endings, black holes honor the universe's unhurried laws. This patience is reflected everywhere. Stars live for millions to billions of years, their fusion balancing gravity's inward pull. When they die, they do so in ways that enrich the universe, spreading heavy elements through supernovae, forming neutron stars and black holes, seeding future generations of stars and planets. Galaxies change shape over eons, merging, growing, settling into new forms. Clusters of galaxies drift within the cosmic web, influenced by the subtle gravity of dark matter we cannot see, but know is there through its effects. All of this unfolds without rush or panic, the universe expressing its nature in slow, deliberate changes. Even time itself is not the same everywhere. Near massive objects, time slows, as measured by observers farther away. This is not speculation but measured fact. Astronauts aboard satellites experience time just a tiny bit differently than people on Earth's surface. Black holes take this to the extreme, freezing time at the event horizon for distant observers. This slowing of time is part of spacetime's breath too, showing that time is woven with space, bending as mass and energy dictate. It is a property, not a background, and it participates in the universe's story. When we observe gravitational waves, we listen to the universe's most subtle sounds. These waves carry information about the masses and spins of merging black holes, about the distances they have traveled, about the history of the cosmos. The fact that we can detect them at all speaks to our growing patience and precision as observers. We have learned to listen for the faintest ripples in the dark, accepting that the universe will not shout its secrets, but will share them quietly with those willing to wait. This willingness to wait is perhaps the greatest lesson of all. We live in a time when answers are expected instantly, when change is demanded quickly. But the universe reminds us that its truest changes are slow, that its greatest structures arose from tiny fluctuations, amplified over billions of years, that even its most violent events, like black hole mergers, take eons to prepare. Nothing in the universe is rushed, and in that slowness there is peace. Black holes themselves, so often imagined as monsters, are simply places where gravity's promise is kept absolutely. They are not evil or violent by choice. They do not seek or hunt. They wait. They hold what comes to them, changing the matter and energy that falls in, perhaps preserving information in ways we are only beginning to imagine. Their existence is not a threat but a fact of nature, one that tells us there are limits to knowing, places where questions must soften into wonder. As you let these thoughts settle, imagine the universe continuing its breath long after we are gone. Stars will be born and die. Galaxies will collide and merge. Black holes will form, grow, and eventually evaporate. Space itself will keep stretching, carrying galaxies apart until they slip beyond view. And through it all, the laws of spacetime will hold, patient and unchanging, writing the universe's history in curves and ripples no matter who is there to read them. Let that vision be a comfort. We are part of this slow breath. Our atoms came from ancient stars. Our lives are measured in moments, but those moments are part of a larger, softer story. When we look up at the night sky, we do not see a void but a living fabric, breathing slowly, telling us that change can be quiet, that endings can be gentle, and that even in darkness there is order and meaning. Imagine light itself growing tired, its energy slowly spent as it travels across the vast spaces between stars and galaxies. It doesn't stop shining all at once. Instead, it stretches and fades, its color shifting towards softer reds as the universe expands around it. This is what scientists call redshift, but you can think of it as light falling asleep, giving in to the universe's patient pull. Light is not lost or destroyed. It simply changes, telling the story of distance, time, and gravity in a gentle language that only the most careful listeners can understand. When a star is born, it ignites with fierce brightness, fusing hydrogen into helium and releasing energy that crosses unimaginable distances. That light leaves the star's surface in all directions, traveling unimpeded unless it meets something along the way. For us on Earth, the sun's light takes about 8 minutes to arrive, a short nap in cosmic terms. But light from other stars can travel for thousands or even millions of years before reaching our eyes. During that journey, it weaves through clouds of gas and dust. It navigates the gentle curvatures of spacetime shaped by gravity, and it stretches along with the expanding universe itself. This stretching is subtle but persistent. The further light travels through expanding space, the more its wavelength increases. Blue light becomes redder and red light grows fainter and cooler. This is not because light slows down. It always travels at the same speed in a vacuum, but because space itself is growing, pulling the waves apart. It is a quiet, unstoppable process, the universe's way of reminding us that even the fastest travelers cannot outrun time. They slow in their own way, not by losing speed but by losing energy. The universe's expansion is not a violent explosion but a gentle inflation of space itself. Every galaxy drifts away from every other on large scales, not because they are flying through space, but because the space between them is stretching. Light must cross this stretching fabric, and in doing so it ages. The cosmic microwave background is the oldest light we can see, released when the universe was only 380,000 years old. Back then, it was brilliant, nearly blinding radiation. Now, after nearly 14 billion years of stretching, it is a faint glow in the microwave range, a lullaby from the universe's infancy. This cosmic background is everywhere. It fills space evenly, a soft afterimage of the Big Bang itself. When we study it, we see tiny fluctuations, small differences in temperature and density that would grow over billions of years into galaxies, clusters, and the cosmic web of filaments and voids. Even in this ancient light, the universe's gentle hand is visible. Those tiny ripples are the seeds of everything we see today, preserved because light carries memory so faithfully, even as it fades. But light does not only fall asleep through cosmic expansion. Gravity itself can pull on light, changing its path and its energy. When light passes near a massive object, a star, a galaxy, a black hole, its path curves. This is gravitational lensing, a quiet bending of light by mass. We see distant galaxies distorted into arcs and rings around closer clusters, like the ripples in a pond around a stone. This lensing is not violent. It is a patient shaping, revealing both the mass that bends the light and the hidden galaxies beyond. Sometimes, this bending is so strong that a single galaxy's light can appear multiple times, taking different paths around a cluster before arriving at Earth. It is like seeing several echoes of the same song, each slightly delayed and shifted in pitch. Astronomers use these echoes to measure the universe's expansion, to map dark matter that cannot be seen directly, and to study the structure of galaxies that would otherwise be too faint. Light, even as it grows tired and stretched, continues to reveal the universe's secrets. Near black holes, this bending becomes extreme. The gravity is so intense that light can orbit the black hole in a perfect circle at the photon sphere. Just outside the event horizon, light can swirl around many times before escaping, if it escapes at all. From a distance, this creates a shadow, a dark circle surrounded by a bright, warped ring of light. The Event Horizon Telescope captured this image for the first time in 2019, showing us the silhouette of a black hole in the galaxy M87. That glowing ring is not the black hole itself, but the last light that manages to escape its gravity's grip. This image is not just a photograph, but a story about light's journey. The photons we see traveled for 55 million years, bent around the black hole's gravity, and were stretched by the universe's expansion before finally reaching our detectors. By the time they arrived, they were tired travelers, their energy spent, their message softened but still clear. They told us about the black hole's mass, about the swirl of matter spiraling inward, about the very shape of spacetime at its most extreme. Even as light stretches and fades, it remains our messenger. It carries information across distances too vast for any physical object to cross in a lifetime. Every star you see in the night sky is a message from the past. Some of those stars may no longer exist, their fuel exhausted, their cores collapsed into white dwarfs, neutron stars, or black holes. But their light remains, arriving at Earth long after their own fires went out. In this sense, light sleep is also a preservation, a way of keeping memory alive across cosmic time. Consider how even our own sun's light will fade. Billions of years from now, it will expand into a red giant, shedding its outer layers into space, forming a planetary nebula that glows softly for a time. The core will remain as a white dwarf, slowly cooling, its light growing ever dimmer over trillions of years. Eventually, it will be a black dwarf, radiating nothing, a cold, dark cinder in an aging galaxy. This is light's ultimate sleep, not an abrupt extinguishing, but a gentle fading, a surrender to time. In the broader universe, galaxies themselves will dim. Star formation will slow as gas is used up. The youngest, brightest stars will die first, leaving only older, cooler ones. Over trillions of years, the universe will become a quieter, darker place. Even black holes will evaporate through Hawking radiation, their mass slowly turning into faint, cold particles escaping into space. This is not an apocalypse, but an unwinding, a final relaxation into stillness. Light falling asleep is the universe's way of showing us that nothing is wasted, nothing is truly lost. Energy is transformed, spread out, shared until it is too diffuse to be gathered again. The second law of thermodynamics says that entropy increases, that energy moves from concentrated to diffuse forms. This is often called the heat death of the universe, but it is not a violent death. It is the slow settling of all things into balance. No part of the universe fights this. It simply allows it, following its own rules without resistance. When we see a sunset on Earth, we witness light falling asleep in miniature. The sun's rays, passing through more atmosphere at that angle, scatter their shorter blue wavelengths away, leaving only the longer reds and oranges. The light we see is tired, stretched, mellowed by its journey. It is a daily reminder of cosmic redshift, a quiet promise that all energy will eventually rest. And yet in that rest is beauty, meaning, and memory. So imagine this. Light crossing billions of light years, traveling for eons, bending around galaxies, passing through expanding space, slowing in color, growing old. It does not resist. It does not complain. It simply continues, carrying the record of everything it has touched. It is the universe's softest voice, whispering across unimaginable distances, reminding us that even in sleep there is truth and wonder. Now let us follow light on its quiet journey even further, tracing how it carries the universe's memory across time and space while surrendering itself slowly to distance, gravity, and expansion. Light is our oldest witness. It records what happens and then travels patiently to deliver its message. When a star flares to life, light bursts outward in every direction, a newborn announcement of its birth. But this light is not a permanent flame. It is a wave, moving outward through space that is itself changing. As it travels, the light's story is edited by time and distance, its energy thinned and softened like ink that fades on parchment left too long in the sun. Imagine a photon leaving a star in a distant galaxy billions of years ago. At that moment, the universe was smaller, the galaxies closer. As space expanded, the distance the photon had to travel grew longer. Yet it did not stop or slow. It was carried along with the stretching universe, its wavelength lengthening, its color shifting redward. What began as a brilliant blue light could arrive here as a pale red glow or even as invisible infrared. This is not destruction but transformation. The energy is conserved, spread more thinly over a wider wave. It is light aging gracefully, falling asleep with dignity. Astronomers use this cosmic redshift to measure distance. By comparing the known properties of certain types of stars or galaxies with their observed brightness and color, they can determine how far away they are and how long ago their light began its journey. In this way, looking out is looking back. Every patch of sky is a time machine. When you see the Andromeda galaxy with the naked eye, you see it as it was over 2 million years ago. The further you look, the older the image becomes, until you reach the cosmic microwave background, the universe's baby picture. The fading of light is not a barrier to knowledge but a window into the past. Gravity also affects light's journey in quieter, more intimate ways. When light passes through clusters of galaxies, its path bends. This gravitational lensing can focus and magnify the light of even more distant galaxies, bringing into view things that would otherwise be lost in darkness. It is a natural telescope created by the universe itself. Light's path is not straight in the traditional sense. It follows the curve of space shaped by mass. In these gentle bends lie clues to the distribution of matter, including dark matter that cannot be seen directly, but reveals itself through its gravitational pull. Strong lensing creates beautiful effects, multiple images of the same galaxy, stretched arcs of light, Einstein rings that encircle massive objects like halos of curved starlight. These phenomena are not distortions in the sense of damage but transformations, light's journey rewritten by the presence of mass. Astronomers read these patterns like fingerprints, reconstructing the mass of lensing galaxies and clusters. In this way, even when light is bent and stretched, it remains a faithful witness, telling the story of gravity's quiet work. Closer to home, light also carries subtle signals of spacetime structure. The Global Positioning System, GPS, relies on the precise timing of light in the form of radio waves, but Earth's gravity affects time itself, slowing clocks slightly compared to those in orbit. Engineers must account for this difference to maintain accuracy. It is a small but real demonstration that gravity and light are intertwined, that even on human scales, spacetime's breath is felt. Light is not just an abstract concept, but a practical tool, its behavior shaped by the same laws that govern galaxies and black holes. And black holes themselves are the most extreme sculptors of light's path. When matter spirals into a black hole, it forms an accretion disk, heating to millions of degrees. The light from this disk is intense, often emitting X-rays as particles collide at nearly the speed of light. Yet even this brilliant light cannot escape if it crosses the event horizon. The horizon is a one-way membrane, a point of no return. Light that crosses it is gone from our universe's view forever. This boundary is not violent in its own frame. It is the inevitable consequence of spacetime's curvature taken to its limit. Outside the event horizon, however, light can escape, but its path is warped. Near the black hole, time slows and space bends so much that light orbits in strange paths. The photon sphere is a region where light can circle the black hole indefinitely if perfectly aimed. Most light eventually either falls in or escapes, but its path is twisted, its energy redshifted. Observers far away see light that is weaker, stretched, softened by its journey out of the gravitational well. This redshift near black holes is not the same as cosmic expansion, but is another way light loses energy, a gravitational redshift, another mode of falling asleep. These behaviors have been tested. Observations of X-ray emissions from matter spiraling into black holes reveal the expected redshifts and broadening of lines that match predictions from general relativity. The first image of a black hole's shadow, captured by the Event Horizon Telescope, shows light bending around the event horizon, forming a glowing ring that maps spacetime's extreme curvature. This light is the last message from matter before it disappears forever, a final whisper across billions of light years. But light's quiet surrender is not limited to individual photons. Entire processes in the universe depend on light's willingness to carry energy and information. Photosynthesis on Earth is one of these processes. Plants capture sunlight, transforming it into chemical energy that fuels life. That light began its journey in the core of the sun, produced by nuclear fusion billions of years in the making, traveled across space, and ended in the gentle capture by a leaf. This is light's gift. It gives without thought of return, delivering energy that nourishes entire ecosystems. In the broader cosmic context, light also cools the universe. As matter collapses into stars and galaxies, it heats up. This heat escapes as light, allowing structures to form. Without the ability to radiate energy away, matter would remain too hot and diffuse to clump together. Light is the universe's way of shedding heat, of allowing the slow formation of complexity from chaos. Even in its departure, light enables creation. Consider, too, the future of light in an expanding universe. As dark energy drives the acceleration of cosmic expansion, distant galaxies will move beyond our observable horizon. The light they emit will be so redshifted that it can no longer be detected, even in principle. The universe will grow dark, not because the light has stopped, but because it has stretched beyond visibility. This is the ultimate sleep of light, not extinguished but so dispersed and softened that it can no longer be gathered. This future is not an apocalypse but a settling. The universe's energy will spread more evenly, entropy increasing as systems move toward balance. Black holes will evaporate through Hawking radiation, releasing their energy back into space in the faintest trickle. Stars will die and not be replaced. The last embers of starlight will fade over unimaginable spans of time. And all the while, light will carry its messages until it can do so no longer, fulfilling its role as the universe's patient courier. Through all of this, light is not destroyed. Energy cannot be destroyed. It is transformed, spread out, cooled, stretched, until it can no longer perform the work it once did. In this ultimate rest is the universe's quiet promise that everything has its time to shine, to travel, to give, and finally to sleep. And in that sleep there is no violence, only the completion of a journey. So when you see a star in the night sky, remember you are seeing ancient light. Light that has traveled uncountable miles, bent around galaxies, stretched through expanding space, and arrived here tired but unbroken. It is a survivor, a messenger, a witness. Its fading is not a loss but a gift, a promise that even the smallest photon carries the story of the universe, and that in its final rest it keeps that story safe. Let us now ease into the final part of this gentle journey, where light's long sleep is not an ending but a transformation into something quieter, deeper, and even more profound. Imagine the universe not as a stage with actors entering and exiting, but as an ocean of energy that constantly shifts from one form to another. In this view, light is the most patient traveler, the courier that accepts every burden and carries it without complaint across impossible distances. But even the courier must rest. Even the message must settle into silence. As the universe expands, the distances between galaxies grow. Galaxies that are gravitationally bound, like the Milky Way and Andromeda, will eventually merge, their stars combining into new forms. But on the largest scales, galaxies not bound together will drift farther apart, carried by the expansion of space itself. Over time, the light they emit will stretch beyond detection, redshifting so much that no observer in the far future will see them at all. The night sky will grow empty of their presence. Not because they vanished, but because their light fell asleep on a journey it could no longer finish. This fading is gentle but relentless. Imagine trying to shout across an endless plain as it grows ever wider. Your voice grows softer, its energy dissipates until it is just a memory of sound in the air. Light behaves the same way in an expanding universe. Its energy spreads thinner, its color shifts to longer wavelengths, until the information it carried is too faint to be gathered. It becomes part of the fabric of space itself, a lingering warmth, a barely measurable murmur. This is the heat death that physicists describe, a universe with maximum entropy, where energy is evenly distributed and can no longer do work. But this death is not an act of violence. It is a settling, a return to balance. Consider the role of black holes in this far future. For trillions of years, they will dominate the landscape of a darkening universe. Stars will have burned out, galaxies will be quiet. Black holes will merge, grow, and then slowly evaporate through Hawking radiation. This evaporation is unimaginably slow for supermassive black holes, taking longer than the current age of the universe by orders of magnitude. But in the end, even these giants will release their stored energy in a faint, cold glow, their own light falling asleep one last time. Hawking radiation itself is light's quiet revenge on the idea of a perfect prison. For so long, we imagined black holes as places where nothing could escape. But quantum mechanics softens this harsh edge. Even black holes cannot hold everything forever. Virtual particles appear near the event horizon, with one falling in and the other escaping. The black hole loses mass this way, its event horizon shrinking slowly, like a candle burning down so slowly you would not notice over 1 billion years. Eventually, it will vanish entirely, leaving behind only the memory of its presence written in the surrounding spacetime. This idea tells us something important about the universe. There are no perfect prisons. Energy moves, transforms, escapes. Light itself, though trapped temporarily, always finds its release eventually. The universe does not allow eternal stagnation. Even the coldest, darkest places will someday surrender their stored energy. This is not hopeful in the usual sense. It does not promise new stars or renewed life. But it is honest. It promises balance. Even in its final sleep, light keeps faith with the universe's laws. When we consider the information carried by light, the story becomes even subtler. Physicists debate whether information is truly lost in a black hole or somehow preserved on its event horizon, possibly encoded in the Hawking radiation itself. This is known as the black hole information paradox. It is not yet fully resolved, but the leading idea is that information cannot be destroyed, even if it becomes inaccessible, scrambled beyond recognition. In this view, the universe is the ultimate archivist. Nothing is ever truly lost. It is only changed into forms we cannot yet read. Imagine that. Every photon that has ever left a star, every bit of radiation emitted by gas spiraling into a black hole, every particle of Hawking radiation that will someday drift into the cold expanse, all of it carries whispers of what came before. These whispers grow faint, disordered, cold, but they exist. They are the universe's way of remembering itself even as it forgets. Light falling asleep does not mean its message is erased. It means its message is entrusted to the quietest corners of spacetime. This vision invites us to consider our own relationship with light. On Earth, we live by its gift. Sunlight warms the planet, drives photosynthesis, powers our weather. Even at night, the sun's light reflected by the moon or scattered in the atmosphere gives us gentle illumination. Our own eyes evolved to see invisible light, a narrow band of the electromagnetic spectrum that our star emits most abundantly. In this way, our senses are tuned to our local environment, to the light that has shaped life for billions of years. But light is not limited to what we see. Infrared, ultraviolet, X-rays, radio waves, all are forms of light. Our instruments extend our senses, letting us see the cold glow of star-forming clouds, the fierce X-ray blasts of black hole accretion disks, the quiet radio whispers of distant galaxies. Each of these signals is light carrying a different part of the story. Each is a traveler that began its journey perhaps before Earth even existed. When we build telescopes, we are not just studying the universe. We are listening to ancient voices arriving after their long sleep. Even our civilization's ambitions are written in light. The data we send through fiber optic cables is light pulsing in glass threads. The signals beamed to satellites and beyond are electromagnetic waves. We speak to our machines and to one another in light, our messages racing around the planet at the fastest speed nature allows. In a way, our thoughts become light, traveling, aging, being received and remembered. The universe's oldest messenger has become ours as well. And yet all this light will eventually fade. Not today, not tomorrow, but over unimaginable spans of time. The stars will die, the galaxies will thin, the black holes will vanish, and the universe will cool. The last light will stretch until it can no longer be distinguished from the gentle hum of empty space. This is not something to fear. It is the universe's promise that nothing is permanent, that everything changes, that rest comes to all things. So as you drift into your own rest, think of the light that has traveled so far to reach you, the starlight that left before humans existed, the photons in your room that bounced from walls and objects to find your eyes, the ancient glow of the Big Bang itself, filling all of space with its soft presence. These are not just physical phenomena. They are reminders that you are part of this vast story, connected by the same gentle rules that guide galaxies and black holes alike. Light falling asleep is not an end. It is a transformation, a surrender to the universe's slow breath. It is the final act of giving, dispersing energy until there is nothing left to give. And in that quiet, in that perfect balance, there is peace. There is the promise that nothing is lost, only changed. That every journey ends not with destruction but with rest. And that even in the coldest darkness, the memory of light remains, woven forever into the fabric of space and time. Imagine a star nearing the end of its life. For most of its existence, it has burned bright, casting light and heat across the darkness of space. The energy of fusion has kept it stable, a delicate balance between the inward pull of gravity and the outward push of radiation. But now, as the star begins to run out of fuel, this balance falters. The core, once so stable, begins to collapse inward under the weight of its own gravity. The outer layers, no longer supported by fusion, begin to drift away, creating a moment of quiet chaos. The star is not dying violently, but quietly and slowly, like a flame gently flickering out. This is the beginning of a process that will lead to some of the most dramatic and awe-inspiring events in the universe. The collapse of a star into a supernova, or in the case of massive stars, the birth of a black hole. The star, which once radiated light that could travel across millions of light years, begins to transform. The process is not abrupt. It is gradual, each stage taking millions to billions of years, with the final moments of the star's life occurring in a flash, a brief but intense burst of energy that marks the end of one chapter in the universe's story. As the core contracts, it heats up to unimaginable temperatures. The outer layers of the star are blown away in a violent but controlled explosion, the supernova. This explosion is not random. It is a natural consequence of the star's inner mechanics. The core, now dense and compact, is crushed under gravity, creating elements heavier than iron in a process known as nucleosynthesis. These elements, carbon, gold, uranium, are forged in the heart of the star, and when the explosion occurs, they are scattered throughout space, enriching the cosmic dust from which new stars, planets, and even life will eventually form. But in this moment of destruction, there is also creation. The memory of the star's death is not lost. It is carried forward, passed down in the elements that are ejected into the cosmos. These elements, once part of the star, are now part of the universe's larger story, scattered across space to be incorporated into new structures. The supernova is a cosmic seed, fertilizing the future of the galaxy, ensuring that the cycle of life and death continues. The collapse of a star may be the end of its life, but it is also the beginning of new life in the universe, as the heavy elements it creates will eventually come together to form new stars, planets, and perhaps even the building blocks of life itself. The energy released in a supernova is so intense that, for a brief time, it outshines the entire galaxy in which the star resides. The explosion sends shockwaves through the surrounding space, triggering the formation of new stars from the gas and dust left behind. These shockwaves are not just the remnants of the star's death, but the catalyst for new beginnings. Just as the star's death was inevitable, so too is the birth of new stars, a cycle that repeats endlessly across the cosmos, as old stars collapse and new ones are born in their place. As we watch the light from distant supernovae, we are not merely observing the death of a star. We are witnessing the creation of the universe itself. The light we see from these events has traveled across space for millions of years, carrying with it the memory of the star's final moments. It is a moment frozen in time, a message from the past that reaches us across the vastness of space, telling the story of a star's collapse and the new life it will bring into being. In this way, the memory of collapsing stars is woven into the very fabric of the universe. It is carried not only in the elements they produce, but in the light they emit, which travels across space to reach us. Every star we see in the night sky is the memory of a collapsed star, a reminder of the violent beauty that shapes the universe. Each photon that reaches our eyes has traveled through time, carrying the story of its origin. We are not just observers of the universe. We are participants in its history, sharing in the light and memory of stars long gone. And yet, even as we marvel at the death of stars, we must remember that this death is not an end but a transformation. The collapsing star's memory does not vanish. It becomes part of the greater story of the universe. The elements created in its core, elements that will eventually form the very building blocks of planets, life, and the universe itself, are the legacy of the star's collapse. This is the universe's way of ensuring that nothing is truly lost. Even in death, there is creation. The collapse of a star may be a quiet, solitary event, but it echoes across the cosmos, shaping the future of galaxies, stars, and life. And as the light from the collapsing star reaches us, we too are reminded of the impermanence of all things. Just as the star will eventually collapse into itself, so too will all things in the universe. Stars are born, live, and die, just as galaxies are formed, evolve, and eventually fade into nothingness. The memory of collapsing stars teaches us that the universe is in a constant state of flux, that nothing remains the same forever. But this impermanence is not something to fear. It is simply the nature of existence, the eternal cycle of birth, life, death, and rebirth. In the end, the memory of collapsing stars is not just about the stars themselves. It is about the universe as a whole, a vast, interconnected web of energy and matter that is constantly changing, constantly evolving. The stars are the universe's storytellers, and their deaths, their collapses, are the chapters that continue to unfold. As we look out at the stars in the night sky, we are not just seeing points of light in the distance. We are seeing the legacy of the stars that have come before, their memories etched in the fabric of space-time, their stories continuing to echo across the cosmos. The cycle of life and death in the universe, driven by the collapse of stars, is not just a process of destruction but a profound act of creation. Every time a star dies in a supernova, it releases a tremendous amount of energy into space, creating new elements and dispersing them across the cosmos. These elements, born in the heart of stars, are the building blocks of everything we know: planets, stars, and even life itself. When we look at the night sky, we are not just seeing distant stars. We are looking at the remnants of ancient explosions, the echoes of long-dead stars, whose energy has been recycled and transformed into new forms over billions of years. Stars are not static objects. They are dynamic, constantly evolving throughout their lifetimes. They go through a series of stages, each one marked by changes in temperature, size, and composition. A star begins its life as a cloud of gas and dust, undergoing gravitational collapse until nuclear fusion ignites its core. For the majority of its life, it will burn hydrogen in its core, shining brightly and providing the energy necessary to sustain life on planets like Earth. But eventually, the star will exhaust its hydrogen fuel. As it ages, it will swell into a red giant, its outer layers expanding to engulf nearby planets. In its final stages, the star undergoes a dramatic transformation. For massive stars, the core will collapse under the force of gravity, and the outer layers will explode in a brilliant supernova. The shockwave from the explosion can trigger the formation of new stars and planets, creating a nebula, a cloud of gas and dust, where new stars are born from the same material that once made up the dying star. For smaller stars, they may end their lives as white dwarfs, their cores slowly cooling over billions of years. These stars, too, contribute to the universe's elemental inventory, but they do so in a quieter, less dramatic way than their more massive counterparts. But the legacy of collapsing stars is more than just the elements they create. It is in the way their deaths shape the future of galaxies and even the very fabric of spacetime. When stars die, they can give rise to black holes, regions of space where gravity is so strong that not even light can escape. These black holes are not just the remnants of a star's life, but key players in the dynamics of galaxies. They influence the movement of stars and gas within their galaxies, and when galaxies collide, their supermassive black holes may eventually merge, sending ripples through spacetime in the form of gravitational waves. These waves, detected by instruments like LIGO, are the subtle vibrations of spacetime itself, generated by the most violent cosmic events. They provide us with a new way of observing the universe, allowing us to listen to the death of stars and the merging of black holes from across the cosmos. Gravitational waves are not just a testament to the power of collapsing stars. They are a reminder that the universe is alive, constantly shifting and changing. Even in its most violent moments, the universe is creating, evolving, and renewing itself. As we study the remnants of collapsing stars, whether in the form of supernovae, neutron stars, white dwarfs, or black holes, we begin to understand the interconnectedness of everything in the universe. Each star's death is a link in a chain of events that stretches back to the Big Bang and extends into the far future. The material that makes up our bodies, the planets we live on, and the stars we see in the sky are all connected through this cosmic cycle. The death of one star is the birth of another. The remnants of ancient stars form the foundation for new generations of stars and planets. In this way, the memory of collapsing stars is not just a record of their past, it is the story of the universe's continuing evolution. And as we look at the stars, we are reminded that everything in the universe is part of this eternal cycle. Our own planet, our own lives, are not isolated events, but part of a much larger cosmic story. The light from distant stars that reaches us is the product of billions of years of cosmic history. That light carries the memory of stars that no longer exist, but whose legacy lives on in the elements they created and the energy they released. Even the Earth itself is a product of the deaths of ancient stars, its composition shaped by the supernovae that occurred long before our solar system was born. The collapse of a star is not an event that happens in isolation. It affects everything around it. When a massive star dies, it sends shockwaves through its surroundings, triggering the formation of new stars and planets. These shockwaves can also spread across galaxies, altering the course of their evolution. The material released during a supernova can form new stars, and the black holes left behind can influence the movement of galaxies for billions of years to come. This interconnectedness is a reminder that the universe is not a collection of isolated objects, but a complex, dynamic system where every action has a ripple effect. The memory of collapsing stars is written in the fabric of the universe. It is in the elements we are made of, the light that reaches us from distant stars and the gravitational waves that ripple through space-time. It is in the way galaxies form and evolve, the way black holes shape their environments, and the way stars give birth to new generations of stars. In this way, the universe is not a static, lifeless place. It is a living, breathing system, constantly changing, constantly evolving. The death of a star is not an end, but a transformation that creates the building blocks for new stars, new planets, and new life. As you gaze up at the stars, remember that you are looking at the memory of collapsing stars. The light you see is not just light. It is a story of creation, transformation, and renewal. It is a reminder that the universe is a dynamic, evolving system, and that the death of one star is the birth of another. In this way, the memory of collapsing stars is the memory of the universe itself, a memory that stretches back to the very beginning and extends into the distant future, continuing to shape the cosmos in ways we are only beginning to understand. As we continue to explore the memory of collapsing stars, we come to understand how these cosmic events have shaped the universe in ways we are only beginning to comprehend. The death of a star is a powerful reminder that the universe is not a place of permanence, but one of constant transformation. Stars are born, live, and die in a never-ending cycle. Their lives, marked by fusion and energy, are temporary, but their deaths leave behind profound legacies that shape the future of galaxies, stars, and even life itself. When a star collapses, it does not simply cease to exist. It creates new forms of matter and energy that will go on to shape the universe in ways that echo far beyond its own lifetime. Supernovae, the explosive deaths of massive stars, scatter heavy elements such as carbon, iron, and gold into the interstellar medium, enriching the gas and dust that will eventually coalesce into new stars, planets, and even the building blocks of life. These elements are the very foundation of everything we know, and without the death of stars, life as we understand it would not exist. In the aftermath of a supernova, the material from the exploded star forms a nebula, a vast, diffuse cloud of gas and dust. Over time, this nebula can collapse under its own gravity, forming new stars and planets from the very remnants of the old star. This process, known as stellar recycling, ensures that nothing in the universe is ever truly lost. Instead, it is transformed, repurposed, and woven back into the fabric of the cosmos. The cycle of star birth, life, and death is a continuous one, and it is through this cycle that the universe evolves, creating ever more complex and diverse structures. The collapse of a star also has a profound impact on the surrounding environment. The shock waves produced by a supernova can trigger the formation of new stars and spark the creation of new galaxies. These shock waves can also accelerate the interstellar medium, causing it to compress and form new molecular clouds, which are the birthplaces of new stars. As the material from the dying star is spread across the cosmos, it becomes part of the larger galactic ecosystem, influencing the formation of future generations of stars, planets, and even life. One of the most fascinating aspects of a star's collapse is the formation of black holes. When a massive star's core collapses, the result is often the creation of a singularity, a point in space where gravity becomes so intense that not even light can escape. This singularity is surrounded by an event horizon, the boundary beyond which nothing can return. The black hole that forms from this collapse is not an isolated phenomenon. It plays a crucial role in the evolution of its host galaxy. Black holes, particularly supermassive black holes found at the centers of galaxies, can influence the motion of stars and gas in their immediate vicinity, shaping the overall structure of the galaxy. Despite their intense gravitational pull, black holes are not the cosmic vacuum cleaners they are often made out to be. They do not go hunting for objects to consume. Instead, they passively interact with their surroundings, drawing in matter that comes too close. Over time, black holes can grow by accreting gas and even merging with other black holes. These mergers, when they occur, release an immense amount of energy in the form of gravitational waves, ripples in spacetime that travel outward, carrying the memory of the black hole's collision. Gravitational waves, detected by instruments like LIGO and Virgo, provide us with a new way of observing the universe. These waves offer insight into the most violent and dramatic events in the cosmos, such as the merging of black holes or the collapse of massive stars. The detection of gravitational waves has opened up a new frontier in astrophysics, allowing us to study cosmic events that were once beyond our reach. Just as light carries information about the universe, so too do gravitational waves, offering a glimpse into the most mysterious corners of spacetime. The memory of collapsing stars is not just carried by light and gravitational waves, but by the very structure of space itself. When a star collapses, it disturbs the surrounding fabric of spacetime, causing ripples that travel outward across the cosmos. These ripples, like the waves on a pond caused by a stone, can be detected millions or even billions of years later. The fact that we can detect these ripples from the collision of black holes is a testament to the far-reaching effects of a star's death. It shows us that the universe is interconnected, that even the most distant events have an impact on the fabric of spacetime. The collapse of a star and the subsequent formation of a black hole are not isolated incidents. They are part of a much larger cosmic story, one that is still unfolding. As we study the remnants of collapsed stars, whether in the form of supernovae, neutron stars, or black holes, we begin to unravel the mysteries of the universe's past and future. These events are the key to understanding the processes that shape galaxies, stars, and planets. They are also crucial to understanding the origins of the elements that make up our world and ourselves. The memory of collapsing stars is carried in the very fabric of space and time. It is written in the light that reaches us, in the gravitational waves that ripple across the cosmos, and in the elements that make up the planets we inhabit. These memories are not just stories of destruction. They are stories of creation, transformation, and renewal. The death of a star is not an end, but a new beginning, a beginning that will continue to shape the universe for billions of years to come. As we look up at the night sky, we are looking at the legacy of stars that have collapsed and died. The light we see is not just the product of a distant explosion. It is a message from the past, carrying with it the memory of a star's life and death. This light has traveled across space for millions or even billions of years, carrying with it the story of the star's collapse, its transformation, and its contribution to the cosmic cycle. In this way, the memory of collapsing stars is not just a record of their death, but a story of the universe's ongoing evolution, a reminder that everything in the cosmos is interconnected, and that death is just another form of change. The concept of infinity is one of the most profound and perplexing ideas that humanity has ever confronted. It is not an abstract notion, but a reality that permeates the universe in ways that we can scarcely comprehend. Infinity is not just an idea found in mathematics. It is present in the very structure of the cosmos, from the endless stretch of space to the infinite possibilities of time. It is both a paradox and a truth that shapes everything we know. In mathematics, infinity is not a number but a concept that describes something that has no end. It is an idea that captures the essence of boundlessness, of something that is unmeasurable and infinite in extent. But while we can conceptualize infinity, we cannot fully grasp it with our senses. It is beyond the reach of our limited experience, beyond the horizons of the observable universe. And yet, infinity is woven into the very fabric of reality, influencing the shapes of galaxies, the cycles of stars, and the paths of particles. The idea of infinity can be traced back to ancient civilizations, where early mathematicians began to contemplate the nature of numbers and the endlessness of space. The Greek philosopher Zeno of Elea posed paradoxes that involved the concept of infinity, showing how the infinite can lead to paradoxical situations. One of his famous paradoxes, known as Achilles and the tortoise, illustrates how an infinite number of steps can seemingly never be completed, even though we know that Achilles will eventually pass the tortoise. This paradox was later resolved through the development of calculus, a branch of mathematics that deals with infinity in a rigorous and practical way. In the modern world, infinity is a cornerstone of much of mathematics and science. It is used to describe the behavior of functions, the limits of sequences, and the nature of the universe itself. In the field of calculus, infinity is used to describe the behavior of functions as they approach a limit. As numbers grow larger, they can approach infinity, yet never truly reach it. This is the concept of limits, and it is the foundation of much of modern physics. In cosmology, infinity plays a critical role in our understanding of the universe. The universe, it seems, is infinite in both space and time. The observable universe, the region of space that we can see and measure, is vast beyond comprehension, but it is only a small fraction of the total universe. The universe itself may stretch infinitely in all directions, with no edge or boundary. This means that the stars, galaxies, and nebulae we see in the sky are only a tiny fraction of what exists in the infinite expanse of space. But infinity is not just a concept of the cosmos. It is embedded in the very structure of spacetime itself. The fabric of spacetime, as described by Einstein's theory of general relativity, is a four-dimensional continuum that stretches infinitely in all directions. The curvature of spacetime, influenced by the mass and energy of objects, shapes the paths that light and matter follow. It is a dynamic, ever-changing system, and infinity is an integral part of its nature. The geometry of spacetime is both finite and infinite, bending and stretching across the universe in ways that we are only beginning to understand. One of the most fascinating aspects of infinity in the universe is the concept of black holes. These regions of spacetime are so dense that they create a gravitational field so strong that not even light can escape. The singularity at the center of a black hole is a point where the curvature of spacetime becomes infinite, where our understanding of physics breaks down. The laws of physics as we know them cannot describe what happens at the singularity, and the infinite density of matter at this point defies our comprehension. Black holes are not just astronomical objects. They are a window into the infinite possibilities of the universe, where the rules we understand no longer apply. But infinity is not limited to the vastness of space or the collapse of matter into black holes. It is also present in the smallest scales of the universe. At the quantum level, particles behave in ways that are governed by the principles of quantum mechanics, and the concept of infinity plays a key role in understanding the behavior of these particles. Quantum mechanics tells us that particles can exist in multiple states simultaneously, a phenomenon known as superposition. This idea of multiple possibilities is a reflection of the infinite potential of the quantum world. The probabilities of where particles might be or what they might do are described by wave functions, which are often expressed as infinite sums of possibilities. In this way, the quantum world is fundamentally connected to the concept of infinity, as particles exist in an infinite number of possible states until they are observed. As we move from the microcosm of quantum mechanics to the macrocosm of cosmology, the concept of infinity continues to guide our understanding of the universe. The infinite nature of space, time, and matter suggests that the universe is far more complex and mysterious than we can fully comprehend. We are but tiny observers, existing in a fleeting moment of time, trying to understand the infinite vastness of the cosmos. But even though we cannot fully grasp infinity, it is a concept that shapes the way we think about the universe and our place in it. Infinity also raises important questions about the future of the universe. If the universe is truly infinite, what lies beyond the observable universe? Will the universe continue to expand forever, or will it eventually contract in a big crunch? Theories about the fate of the universe depend on the nature of infinity and the forces that govern the cosmos. The discovery of dark energy, which is driving the acceleration of the universe's expansion, has added a new layer of mystery to the question of infinity. If the expansion continues indefinitely, the universe will become colder and darker over time, with stars dying out and galaxies drifting apart. This concept of an infinite, cold, dark universe is known as the heat death, a potential end state in which all the energy in the universe is evenly distributed and no processes can occur. It is a sobering thought, but it also reflects the paradox of infinity, the idea that even in the most extreme scenario, the universe will continue to exist in some form, stretching forever into the unknown. But despite the coldness and emptiness that might await the universe in the distant future, there is something comforting about the idea of infinity. It suggests that the universe is eternal, that it has no beginning or end. It is a vast, endless expanse that has been unfolding for billions of years and will continue to do so for billions more. In this sense, infinity provides a sense of permanence and continuity, a reminder that the universe is both infinitely complex and infinitely enduring. In the end, the quiet mathematics of infinity is not just a concept for mathematicians or physicists to ponder. It is a profound reflection of the universe itself, a mirror that reflects the mysteries of existence. Infinity is present in the stars, in the galaxies, in the quantum particles that make up all matter. It is woven into the very fabric of spacetime, guiding the expansion of the universe and the formation of stars and planets. And while we may never fully understand the vastness of infinity, it is a concept that will continue to inspire awe and wonder as we look to the stars and contemplate our place in this infinite cosmos. As we continue to explore the quiet mathematics of infinity, we find ourselves confronting not just the vastness of the universe, but the very foundations upon which it is built. Infinity is not a simple concept to grasp. It is, in many ways, an abstraction that challenges our understanding of the physical world. Yet, it is woven into the fabric of everything that exists, from the infinitely small particles of quantum mechanics to the infinite expanse of the cosmos. Infinity exists not just as a number, but as a relationship between the finite and the infinite, between the measurable and the immeasurable. And in this relationship, we begin to see how the universe itself behaves. At the smallest scales, infinity is embedded in the quantum world. Quantum mechanics reveals that the universe is not composed of solid, indivisible units, but of waves and probabilities. Particles are described by wave functions, which tell us the probability of finding a particle in a particular location at any given time. These wave functions are often expressed as infinite sums, with an infinite number of possibilities existing until the moment of measurement. This notion of superposition, the idea that particles can exist in multiple states at once, emerges from the infinite potential of the quantum world. It suggests that the universe is not static, but in a constant state of flux, where every possibility exists simultaneously until it is observed. In this sense, the quantum realm is a space where infinity is not just a concept but a driving force that shapes the behavior of particles and fields. The infinite possibilities of the quantum world are at odds with the familiar classical view of the universe, where objects have definite positions and velocities. In the classical world, the idea of infinity is more abstract, used to describe things that are beyond measure, distances that are too vast, times that are too long, and energies that are too great to quantify. For example, the idea of infinite space is central to cosmology. The universe is vast, stretching across billions of light years, and yet in a way it seems to have no boundaries. The observable universe is the region that we can see and measure, but beyond that, space stretches infinitely. This infinity is not just a mathematical construct but a physical reality. As far as we can observe, the universe seems to be expanding, with galaxies moving away from us at increasing speeds. The rate of this expansion suggests that the universe is not only infinite but also growing, as space itself stretches and expands. This process, known as cosmic inflation, occurred in the moments immediately after the Big Bang, when the universe rapidly expanded from a single point to the vast expanse we see today. But while space may appear to stretch infinitely, the concept of infinity becomes more elusive when we consider the fabric of spacetime itself. According to Einstein's theory of general relativity, spacetime is a dynamic, malleable entity that is shaped by the mass and energy of objects within it. Spacetime is not a fixed backdrop against which events unfold. It is an active participant in the universe's evolution. Mass and energy bend spacetime, creating gravitational fields that influence the motion of planets, stars, and even light. This curvature of spacetime gives rise to phenomena such as black holes, regions where spacetime is warped so severely that not even light can escape. The singularity at the center of a black hole is a point where the curvature of spacetime becomes infinite, where the laws of physics as we know them break down. This is the point at which infinity becomes more than just a theoretical concept. It becomes a physical reality. Black holes are not just theoretical constructs. They are real objects in the universe that shape the galaxies in which they reside. Supermassive black holes sit at the centers of most large galaxies, including our own Milky Way. These black holes have masses millions or even billions of times that of our Sun, and their gravitational influence extends across vast distances. They shape the orbits of stars, control the flow of gas and dust in their vicinity, and are even thought to regulate the growth of galaxies themselves. The presence of a supermassive black hole at the center of a galaxy can influence star formation, prevent gas from accumulating in the galactic core, and even determine the ultimate fate of the galaxy. In this way, black holes are not just objects of fascination. They are crucial players in the cosmic drama, shaping the evolution of galaxies and, by extension, the universe. The behavior of black holes is not only a testament to the power of gravity, but also a window into the nature of infinity itself. As a black hole consumes matter, it accumulates mass and energy, but it also distorts spacetime around it, creating a well of gravity that nothing can escape. This process of accretion is a slow, steady growth that continues for billions of years. As a black hole grows, its event horizon, the boundary beyond which nothing can escape, expands. And yet, despite this expansion, the black hole itself remains an enigma. We cannot directly observe what happens beyond the event horizon, as light and matter are trapped within it. What happens inside the event horizon is a mystery, but it is a mystery that points to the infinite nature of the universe. The singularity at the center of a black hole is a point where our understanding of physics breaks down, where spacetime itself becomes infinitely curved, and where the laws of nature as we know them cease to apply. This idea of infinity challenges our understanding of the universe and our place within it. We are accustomed to thinking of the universe as a place that can be measured, quantified, and understood through observation and experimentation. But infinity defies our attempts to measure it. The concept of infinity is not just a mathematical abstraction. It is a real feature of the universe. It shapes the behavior of galaxies, stars, and black holes, and it is woven into the very fabric of spacetime. Infinity tells us that the universe is not finite, that there are no boundaries to space, no limits to time. It suggests that the cosmos is not a static, closed system, but an ever-expanding, dynamic entity that stretches out into the unknown. This is the quiet mathematics of infinity, a concept that underpins everything we know about the universe, from the vastness of space to the strange and mysterious behavior of black holes. It is a reminder that the universe is not simply a collection of objects. It is a dynamic, evolving system, one that is shaped by the infinite potential of spacetime itself. As we explore the universe, we continue to encounter the infinite, whether it is in the distance between galaxies, the behavior of light near black holes, or the way time stretches and bends under the influence of gravity. Infinity is not just a concept to be studied. It is the very essence of the universe, a reminder that the cosmos is both boundless and eternal, a place where the possibilities are truly limitless. Infinity, as a concept, presents a challenge not only to our understanding of the universe, but also to our deepest philosophical reflections on existence itself. We tend to view the universe as something finite, something measurable, Our lives are finite, our planet is finite, even our understanding of time has limits. Yet, infinity is embedded in the very structure of reality, from the infinitesimal to the grandest scales. The realization that space, time, and matter stretch infinitely is both humbling and awe-inspiring. It means that there is always more to discover, that there is no ultimate boundary to the cosmos, and that our understanding of the universe is always incomplete, always expanding. The question of whether the universe is truly infinite is one that has puzzled scientists for centuries. The observable universe, the part of the cosmos that we can see with our telescopes and instruments, is vast beyond comprehension, but it is not the entire universe. It is simply the region from which light has had enough time to reach us since the Big Bang. Beyond this horizon, there may be an infinite expanse, stretching farther than our current instruments can detect. The universe may continue forever, with galaxies and stars existing far beyond the limits of our vision. If this is true, it suggests that the universe has no edge, no boundary, and no end. It is a vast, endless space that continues to unfold, expanding forever into the unknown. But even if the universe is infinite, it is not static. The expansion of the universe is a key piece of evidence that tells us the cosmos is dynamic, always changing. Since the Big Bang, space itself has been stretching, carrying galaxies farther and farther apart. This expansion is not a force pushing galaxies apart but a stretching of space itself. It is as if the very fabric of spacetime is being stretched, creating more space between the galaxies as it does. This expansion is not only observable in the movement of galaxies, but is also evident in the way light travels through the universe. As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum, a phenomenon known as cosmological redshift. The discovery of the accelerating expansion of the universe, driven by a mysterious force called dark energy, has added another layer of complexity to our understanding of infinity. If the expansion continues indefinitely, the universe will become colder and darker over time. The stars will burn out, galaxies will drift apart, and the universe will eventually enter a state of near absolute zero, where no processes can occur. This scenario, known as the heat death of the universe, is one possible fate of an infinite universe. In this scenario, infinity is not just a concept of size or time, but of entropy, a state of maximum disorder, where everything is spread out evenly and no energy remains concentrated enough to do work. But the fate of the universe may not be as simple as an endless, cold expansion. Some theories suggest that the universe could eventually stop expanding and begin to contract, eventually collapsing in on itself in a big crunch. In this scenario, the universe would return to a singular state, much like the one from which it originated. This cyclical model of the universe, where the cosmos expands and contracts infinitely, has been proposed by several cosmologists. If this is true, it suggests that the universe is not truly infinite, but rather a series of infinite cycles, each one giving birth to a new universe, each with its own Big Bang and eventual collapse. The concept of infinity also plays a crucial role in the study of black holes. As mentioned earlier, black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. At the center of a black hole lies a singularity, a point where the curvature of spacetime becomes infinite and the laws of physics as we know them break down. The singularity represents the ultimate manifestation of infinity, a place where time and space lose all meaning. It is a region where the very fabric of the universe is torn apart, and where our understanding of reality no longer applies. Yet, despite the mysteries of the singularity, black holes themselves are not purely destructive forces. They play a crucial role in the formation and evolution of galaxies, and they serve as a reminder that infinity can be both a source of creation and destruction. Interestingly, black holes are not just cosmic objects, they are also cosmic laboratories. Scientists study the behavior of matter near black holes to better understand the laws of physics, particularly the nature of gravity and quantum mechanics. The event horizon of a black hole is the point beyond which nothing can escape, not even light. But this boundary also serves as a window into the deeper workings of the universe. As matter falls toward a black hole, it is heated to extreme temperatures, emitting radiation that scientists can observe. This radiation, known as Hawking radiation, is emitted by black holes and is one of the key phenomena that helps us study these enigmatic objects. The fact that black holes can emit radiation, something that was once thought impossible, serves as a reminder that even in the most extreme conditions, the universe can still surprise us. The quiet mathematics of infinity also extends to the realm of theoretical physics. One of the most intriguing ideas in modern physics is the multiverse theory, which posits that there are potentially infinite universes, each with its own set of physical laws and constants. If this theory is correct, it suggests that the universe we inhabit is just one of many, and that there are infinitely many versions of reality, each existing in its own separate dimension. This idea challenges our fundamental understanding of existence and suggests that infinity is not just a characteristic of space and time, but also a fundamental feature of reality itself. The concept of the multiverse raises profound questions about the nature of reality, the limits of human knowledge, and the possibility of parallel worlds existing alongside our own. In this context, infinity is not just a concept for mathematicians and physicists to debate. It is a key to understanding the very nature of existence. It challenges our perceptions of space, time, and reality, and it forces us to confront the limits of our understanding. The infinite expanse of the cosmos, the infinite possibilities of quantum mechanics, and the infinite potential of mathematical relationships all point to the fact that the universe is far more complex and mysterious than we can fully comprehend. Infinity is not just a number, but a lens through which we can explore the deepest questions about the universe and our place in it. The quiet mathematics of infinity is a journey into the unknown, a search for understanding in a universe that is, at its core, infinitely vast and complex. Whether we are contemplating the infinite stretch of space, the infinite possibilities of quantum mechanics, or the infinite cycles of the cosmos, infinity reminds us that the universe is a place of endless mystery, where every answer leads to more questions. It is a reminder that the universe is not a static, closed system, but a dynamic, ever-expanding cosmos, where infinity is not just a concept to be studied, but a reality to be experienced. The universe, in its vastness, is full of mysteries that continue to elude us. One of the most profound and enigmatic of these is the phenomenon of Hawking radiation. Named after the physicist Stephen Hawking, who predicted its existence in 1974, this radiation offers a glimpse into the heart of black holes, those enigmatic regions of space where gravity is so strong that not even light can escape. Hawking's discovery challenged our understanding of the laws of physics and suggested that black holes, rather than being eternal prisons for matter, might eventually evaporate over time. Hawking's insight came from combining the principles of quantum mechanics with general relativity, two theories that, at first glance, seemed incompatible. Quantum mechanics describes the behavior of particles on the smallest scales, while general relativity governs the behavior of large-scale objects like stars and galaxies. These two theories were thought to operate independently, with quantum mechanics working on the subatomic level and general relativity working on the cosmic scale. But when applied to black holes, Hawking realized that the two theories could not be separated. At the heart of a black hole lies a singularity, a point of infinite density where spacetime curves infinitely and the laws of physics break down. This singularity is surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. According to classical physics, once something crosses the event horizon, it is lost forever. But Hawking realized that this was not the case. Instead of a perfect boundary, the event horizon has a strange, quantum mechanical property. It is constantly fluctuating. These fluctuations create pairs of particles, one with positive energy and the other with negative energy, which briefly appear and then annihilate each other. However, near the event horizon, these fluctuations can be affected by the immense gravitational forces of the black hole. If a particle-antiparticle pair forms near the event horizon, the black hole's gravity can separate them, with one particle falling into the black hole and the other escaping into space. The particle that escapes is what we observe as Hawking radiation. The energy for this radiation comes from the black hole itself. As the escaping particle carries away energy, the black hole loses mass, and over time this process leads to the gradual evaporation of the black hole. This radiation is incredibly faint, making it almost impossible to detect directly. For large black holes, the amount of radiation emitted is so small that it is practically negligible. However, for small black holes, the radiation is much stronger, and they could potentially evaporate completely over time. This led to a radical new idea in theoretical physics. Black holes, far from being eternal, could eventually disappear. The implications of this discovery are profound, as they suggest that black holes are not the end of the line for matter and energy, but rather a transitional phase in the universe's ever-changing landscape. The idea that black holes can evaporate challenges our understanding of the fate of information that falls into them. According to classical physics, once something crosses the event horizon, it is lost forever. But the concept of Hawking radiation suggests that information is not entirely lost. Instead, it is transferred to the radiation that escapes from the black hole. This has led to the so-called black hole information paradox, a major puzzle in theoretical physics that remains unresolved. If information can escape a black hole via Hawking radiation, it raises questions about how this information is encoded and whether it can be recovered in some form. Hawking's discovery has profound implications for our understanding of the universe. It suggests that the very fabric of space and time is not as solid and unchanging as we once thought. The event horizon of a black hole, once considered a hard, unyielding boundary, is now understood to be a dynamic, fluctuating region where quantum mechanics and gravity intertwine. This revelation has opened up new avenues of research in both quantum physics and cosmology, as scientists seek to understand the true nature of black holes and the ultimate fate of the information they contain. The study of Hawking radiation is also important for our understanding of the early universe. In the moments after the Big Bang, the universe was a hot, dense place filled with extreme temperatures and energies. During this time, small black holes could have formed, and the radiation they emitted could have played a role in the evolution of the cosmos. If black holes can evaporate through Hawking radiation, they may have contributed to the formation of the cosmic structures we see today, adding another layer of complexity to our understanding of the universe's origins. Yet despite its significance, the concept of Hawking radiation remains largely theoretical. We have not yet observed this radiation directly, and detecting it from a distant black hole is a daunting challenge. The radiation emitted by black holes is incredibly faint, and the presence of a black hole is difficult to detect unless it is actively pulling in matter from its surroundings. Moreover, the radiation is at a very low temperature, making it difficult to measure with current technology. Nevertheless, the implications of Hawking's work continue to inspire scientists and astronomers to explore new ways to detect and study this elusive phenomenon. In the larger context of physics, Hawking radiation connects quantum mechanics and general relativity in a way that no other theory has done before. It highlights the importance of understanding both the smallest and largest scales of the universe. Quantum mechanics governs the behavior of the smallest particles, while general relativity describes the behavior of massive objects like black holes and galaxies. By linking these two theories, Hawking provided a glimpse into the potential future of physics, a future where the fundamental forces of the universe are unified into a single, coherent theory. As we continue to explore the mysteries of the cosmos, Hawking radiation serves as a reminder that the universe is full of surprises. It challenges our assumptions about black holes, gravity, and the very nature of space and time. It suggests that even in the most extreme regions of the universe, where we thought the rules of physics no longer applied, there is still much to learn. In this way, Hawking's discovery not only expanded our understanding of black holes, but also opened up new frontiers of exploration in the search for a unified theory of everything. Through Hawking's work, we have learned that the universe is not a place of absolutes. Even the most stable and seemingly immutable objects, like black holes, are subject to change and evolution. The idea that black holes can evaporate and eventually disappear is a profound reminder that nothing in the universe is truly permanent. As we continue to study the cosmos, we are reminded that the universe is not static, but a constantly evolving, ever-changing entity, where even the most established principles are subject to revision in light of new discoveries. As we venture deeper into the implications of Hawking radiation, it becomes evident that this discovery not only challenges our understanding of black holes, but also invites a radical rethinking of the very nature of space, time, and energy. The revelation that black holes could slowly evaporate over time, gradually losing mass as they emit radiation, leads us to a profound realization about the universe's most mysterious objects. The black hole, once thought of as a one-way trap for matter and light, now becomes a complex system of energy exchange, where even the most seemingly permanent structures of the universe are subject to the flow of time and entropy. This concept of evaporation challenges the classical view of black holes as absolute objects, which once captured matter, kept it forever, and prevented any escape. Hawking's idea that black holes can radiate energy implies that they are not permanent fixtures in the universe. Their presence, although immense and powerful, is finite. Over vast periods of time, a black hole can lose enough mass through Hawking radiation to eventually disappear, leaving behind only the faintest traces of its existence. The idea that these celestial giants, once considered eternal, may eventually die is both humbling and enlightening. It serves as a reminder that nothing in the universe is truly indestructible, and even the most massive objects are susceptible to the passage of time. The evaporation of black holes also raises important questions about the fate of information that falls into them. The famous black hole information paradox arises from this issue. If a black hole can evaporate, what happens to the information contained within it? According to the laws of quantum mechanics, information cannot be destroyed. However, if a black hole evaporates and disappears, it seems as though the information inside it is lost forever. This paradox has led to one of the most significant debates in modern physics, as scientists continue to search for a resolution. Some theories suggest that the information is not lost, but encoded in the radiation emitted by the black hole, while others propose that it is stored in a quantum form at the event horizon, the boundary around the black hole. The answer to this question remains elusive, but it speaks to the fundamental tension between quantum mechanics and general relativity, two theories that govern the behavior of the universe on vastly different scales. Hawking's prediction of black hole evaporation also points to a deeper connection between the laws of thermodynamics and the behavior of gravity. In classical thermodynamics, energy is conserved and entropy, or disorder, always increases. The second law of thermodynamics states that the total entropy of a closed system will never decrease, but in the case of black holes, this was not immediately clear. The information paradox arises from this conflict. If the information inside a black hole is lost during its evaporation, it would imply that entropy could decrease, violating the second law. However, Hawking's radiation offers a resolution to this problem. It suggests that the entropy of a black hole, rather than being lost, is encoded in the radiation it emits. This new understanding not only sheds light on the behavior of black holes, but also offers a potential pathway to reconciling the differences between quantum mechanics and general relativity. Moreover, the process of black hole evaporation and the role of Hawking radiation deepen our understanding of the universe's ultimate fate. If black holes can slowly evaporate, what does this mean for the long-term future of the cosmos? The discovery that black holes can die by emitting radiation implies that the universe is not a static, unchanging place, but a dynamic and evolving system. The gradual evaporation of black holes over incredibly long timescales suggests that, in the distant future, the universe may be a much different place than it is today. Stars will burn out, galaxies will drift apart, and even the black holes themselves will eventually vanish. The universe will continue to expand, but as it does, it will become colder and darker, ultimately reaching a state where no energy is concentrated enough to do work. This is known as the heat death of the universe, a scenario where entropy has reached its maximum, and all that remains is a vast, empty expanse of cold space. Yet, even in the face of such an eventuality, Hawking's theory of black hole evaporation provides a glimpse of something deeply profound. It suggests that even in the most extreme environments, there is a continuous flow of energy and information. The universe, it seems, is not a place of absolute endings, but of transitions, of constant change and transformation. The death of a black hole, rather than being a moment of finality, is part of a larger, ongoing process of evolution and renewal. The energy that once resided in the black hole is not lost, but is carried forward into the universe in a different form, in the form of Hawking radiation. This radiation, though faint, is a remnant of the energy once trapped by the black hole, and it continues to influence the universe long after the black hole has evaporated. This idea challenges the traditional view of the universe as a closed system, where energy is locked away in places where we cannot access it. Instead, the universe is a system of interconnected processes, where even the most isolated objects are part of a larger flow. The energy that was once confined to a black hole is now released back into the cosmos, ready to participate in new processes of creation. In this sense, black holes, far from being destroyers of energy, are actually creators of new forms of energy and new possibilities for the universe to evolve. Hawking radiation, then, is not just a theoretical prediction about the behavior of black holes. It is a window into the deepest workings of the universe. It invites us to reconsider our notions of time, space, and entropy. It asks us to think about the universe not as a static, unchanging place, but as a dynamic, ever-evolving system, where even the most extreme objects like black holes are part of a much larger and more intricate process. The fact that a black hole can emit radiation and eventually evaporate shows us that nothing in the universe is truly permanent. Even the darkest, most mysterious objects in the cosmos are subject to the flow of time, to the inexorable march of entropy. As we study Hawking radiation and the implications of black hole evaporation, we are drawn into a deeper understanding of the universe itself. The concept of a universe that is constantly changing, constantly evolving, and ultimately finite is a humbling reminder of our place in the cosmos. It challenges our assumptions about the permanence of objects and the fate of the universe. And yet, it also offers a sense of hope, because, in the end, the universe is not a place of finality, but a place of endless transformation. Hawking's work gives us a glimpse of a universe that is never truly still, always moving, always evolving. And in that movement there is beauty, there is wonder, and there is the possibility of new beginnings, even in the most unexpected places. As we delve deeper into the concept of Hawking radiation, it becomes clear that the implications extend far beyond our understanding of black holes and their eventual fate. The possibility that black holes could eventually evaporate challenges the very nature of time, entropy, and the life cycle of the universe itself. What Hawking's discovery suggests is that even the most extreme regions of spacetime, where the laws of physics are thought to break down, are not beyond the reach of the universe's natural flow, its cycle of creation, transformation, and eventual decay. The process of black hole evaporation, driven by Hawking radiation, forces us to rethink the concept of what it means for something to disappear or be lost in the universe. In classical physics, when something falls into a black hole, it is lost forever. Its information, its mass, and its energy are trapped. Yet, as Hawking's theory proposes, even black holes must surrender their mass to the universe through the radiation they emit. This insight leads to a profound question in physics. What happens to the information that falls into a black hole? If it can escape through Hawking radiation, does this mean that information is never truly lost? This paradox, often called the black hole information paradox, raises critical questions about the nature of reality itself, the permanence of information, and the limits of our understanding of physics. If black holes, those cosmic behemoths, can eventually evaporate and release energy, this suggests that nothing in the universe is ever truly permanent. Even objects that seem unchanging, like black holes, will eventually fade, losing their mass and energy, and in doing so, influencing the very fabric of spacetime. This gradual decay of black holes through Hawking radiation serves as a reminder that the universe is not a static, unchanging place, but a dynamic, evolving system. Nothing, not even the most powerful forces in the cosmos, can escape the effects of entropy, the tendency for systems to move toward disorder. The concept of entropy is central to our understanding of the universe, and the eventual evaporation of black holes through Hawking radiation is a reflection of this fundamental law. Hawking radiation also has profound implications for the study of thermodynamics. The discovery that black holes can emit radiation suggests that black holes possess entropy, a property once thought to be reserved for ordinary matter. In the 1970s, Jacob Bekenstein, building on Hawking's work, suggested that black holes could have entropy proportional to the surface area of their event horizon, a concept that became known as the Bekenstein-Hawking entropy. This was a groundbreaking insight, as it bridged the gap between gravity and thermodynamics. For the first time, it suggested that black holes, long thought to be purely gravitational objects, also have thermodynamic properties like temperature and entropy, and thus play a role in the larger dance of energy and matter in the universe. The connection between Hawking radiation and entropy also opens the door to a deeper understanding of the nature of spacetime itself. The more we learn about the quantum properties of black holes, the more we begin to question the very structure of space and time. Quantum mechanics, which governs the behavior of subatomic particles, has long been at odds with general relativity, the theory that describes the gravitational force on a cosmic scale. The discovery of Hawking radiation represents a rare point where these two theories converge, offering a glimpse of what a unified theory of quantum gravity might look like. In essence, Hawking radiation shows that the quantum properties of spacetime have real, physical consequences on the largest, most massive objects in the universe. Moreover, the idea that black holes are not permanent also forces us to reconsider the future of the universe itself. If even black holes, those colossal, seemingly eternal objects, can eventually fade away, what does this mean for the long-term fate of the cosmos? The universe, as we understand it, is constantly expanding, and the fate of the universe is tied to the evolution of stars, galaxies, and black holes. If the expansion of the universe continues indefinitely, as current observations suggest, then the energy within the universe will eventually be spread out so thinly that no further work can be done. This scenario, known as the heat death of the universe, paints a picture of a universe where all energy is uniformly distributed and no processes can occur. In this dark, cold future, even the remnants of black holes will evaporate, and the universe will be left in a state of maximum entropy, with no structure or activity remaining. This potential future of the universe is one where time itself stretches out infinitely, yet nothing occurs. The universe will become an immense, dark, and empty space, and the stars that once shone so brightly will be long gone. However, even in this final stage, there is a certain poetic symmetry in the idea that the universe's last moments will be governed by the principles of Hawking radiation. Even in its quiet death, the universe will continue to follow the rules of quantum mechanics and thermodynamics, with the energy released by black holes returning to the cosmos in a faint, almost imperceptible manner. The quiet decay of black holes, driven by Hawking radiation, is not just the end of one process but the beginning of another. It serves as a reminder that the universe is a dynamic system, always in motion, constantly changing. Even the most fundamental objects in the universe, those that seem unchanging and eternal, are subject to the passage of time and the inexorable forces of entropy. The concept of Hawking radiation forces us to look beyond the immediate and the tangible, to consider the long-term implications of the universe's evolution. It challenges our understanding of permanence and invites us to reflect on the inevitable decay and renewal that are the hallmarks of the cosmos. In this way, the study of Hawking radiation opens up a larger conversation about the nature of time, space, and the fate of the universe. While we may never fully understand the ultimate fate of the cosmos, we are given a glimpse of the infinite possibilities that lie ahead. The quiet echoes of Hawking radiation remind us that the universe is not a place of finality, but a place of endless transformation, where even the most powerful forces are subject to the passage of time. The discovery of Hawking radiation is a testament to the power of human curiosity and the relentless quest for knowledge. As we continue to explore the mysteries of the cosmos, no matter how vast or distant. The universe is a vast, intricate web of stars, galaxies, and black holes, each playing a unique role in the ongoing story of creation and destruction. Among these cosmic objects, black holes stand out as some of the most mysterious and powerful entities in existence. Once thought of as mere cosmic vacuum cleaners, black holes are now understood to be far more than that. In fact, they play a crucial role in shaping the structure of galaxies, acting as cosmic gardeners, nurturing the birth of new stars and planets, and ensuring the continuity of the cosmic cycle. A black hole is born when a massive star collapses under the force of its own gravity. The core of the star becomes so dense that it forms a singularity, a point in space where the laws of physics as we know them cease to apply. This singularity is surrounded by an event horizon, the boundary beyond which nothing, not even light, can escape. The immense gravitational pull of a black hole is so powerful that it warps the fabric of spacetime itself, creating a region where time and space are stretched and distorted. But black holes are not the destructive, all-consuming entities they were once thought to be. In fact, they are the cradles of galaxies, the very heart of cosmic evolution. At the centers of most galaxies, including our own Milky Way, resides a supermassive black hole, its mass millions or even billions of times greater than that of the Sun. These supermassive black holes are not just passive objects, they are active players in the life cycles of galaxies. They regulate the formation of stars, control the growth of galaxies, and even influence the distribution of matter within their cosmic neighborhoods. The process by which black holes shape galaxies is a delicate balance between creation and destruction. As a supermassive black hole feeds on gas, dust, and other matter, it releases enormous amounts of energy in the form of radiation. This radiation can heat up the surrounding gas, preventing it from collapsing into new stars. In this sense, black holes act as cosmic gardeners, trimming back the growth of their galactic gardens, ensuring that the pace of star formation remains steady. Without the regulating influence of these black holes, galaxies could become overrun with new stars, depleting the gas and dust necessary for further star formation. At the same time, black holes are also responsible for the creation of new stars. As they consume matter, they expel powerful jets of energy and particles that can trigger the collapse of nearby gas clouds, sparking the birth of new stars. This feedback loop between the black hole and its surrounding environment creates a dynamic system in which the black hole both nurtures and constrains the growth of the galaxy. In this way, black holes are not just destroyers, but also creators, shaping the very structure of the universe in which we live. One of the most fascinating aspects of black holes is the way they influence the flow of gas and matter within their host galaxies. The gravitational pull of a black hole can create enormous accretion disks, vast whirlpools of gas and dust that spiral inward toward the event horizon. As this matter falls in, it heats up to millions of degrees, emitting intense radiation that can be detected by astronomers across vast distances. These accretion disks are not only a source of incredible energy, but also a key factor in the formation of stars and galaxies. In the region surrounding a black hole, the gravitational forces are so strong that they warp the fabric of spacetime itself. This warping causes light to bend, creating a phenomenon known as gravitational lensing. Gravitational lensing allows astronomers to observe distant galaxies and objects that would otherwise be invisible, providing a unique window into the structure of the universe. The presence of a supermassive black hole at the center of a galaxy also influences the motion of stars and gas within the galaxy. Stars orbiting near a black hole move at incredible speeds, their orbits shaped by the gravitational pull of the black hole. In this way, black holes act as cosmic anchors, holding entire galaxies together and controlling their motion. The relationship between black holes and galaxies is not just one of mutual influence. It is also a relationship of cosmic feedback. The energy emitted by black holes, particularly in the form of jets of particles and radiation, can affect the surrounding gas, preventing it from collapsing into new stars. This feedback mechanism ensures that the rate of star formation in galaxies remains balanced, preventing the galaxy from becoming overcrowded with stars. At the same time, the energy from black holes can also trigger the collapse of nearby gas clouds, leading to the creation of new stars. In this way, black holes are not just destroyers but also gardeners, shaping the growth of their galactic gardens and ensuring the continued evolution of their host galaxies. One of the most intriguing aspects of black holes as cosmic gardeners is the role they play in the formation of supermassive black holes in the centers of galaxies. Scientists believe that these supermassive black holes may have formed early in the history of the universe, during the earliest stages of galaxy formation. As galaxies merged and gas clouds collapsed, black holes may have grown rapidly, feeding on the surrounding matter and growing to enormous sizes. The growth of these supermassive black holes may have been a key factor in the formation of the galaxies themselves, as their gravitational influence helped to shape the structure of the galaxy and regulate its growth. The relationship between black holes and galaxies is still an area of active research. While much has been learned about the ways in which black holes influence the growth and evolution of galaxies, there is still much we do not understand. For example, how do black holes grow to such enormous sizes? What role do they play in the formation of galaxies? And what happens when two galaxies, each with its own supermassive black hole, collide? These are questions that scientists continue to investigate, using both observational data and computer simulations to model the behavior of black holes and their effects on galaxies. Despite the many mysteries that remain, one thing is clear: black holes are far more than just the cosmic destroyers they were once thought to be. They are the cradles of galaxies, the gardeners that shape the growth and evolution of the universe. Without black holes, the universe would be a very different place. The balance they strike between creation and destruction, between growth and regulation, is essential to the continued existence of galaxies and stars. And as we continue to study these mysterious objects, we are reminded that the universe is not just a place of chaos and entropy, but also a place of incredible order and structure, with black holes at the heart of it all. The cosmic gardens cultivated by black holes are not simply confined to their immediate surroundings. In fact, the influence of supermassive black holes extends across vast stretches of space, reaching into the very heart of galaxies. The role of black holes in shaping the evolution of galaxies is far-reaching, with their gravitational forces dictating the motion of stars and gas clouds, their energy output regulating the pace of star formation, and their mergers creating cosmic upheavals that ripple through the galaxy's structure. These quiet gardeners work on a scale that is almost incomprehensible, with their influence extending over millions, if not billions, of light years. As we observe the interplay between black holes and their galaxies, it becomes clear that these objects do more than simply serve as anchors. They are the engines of cosmic evolution, playing an active role in sculpting the landscapes of their host galaxies. The energy they emit, whether through radiation, superheated jets of particles, or the process of accretion, drives the growth and development of the galaxies they inhabit. This energy is released in bursts, creating a feedback loop that can either stimulate or inhibit star formation. In some cases, the intense radiation from a black hole's accretion disk can heat the surrounding gas, preventing it from collapsing to form new stars. In other cases, the shock waves generated by the black hole's energy can compress gas clouds, triggering the birth of new stars and stellar systems. This constant push and pull between creation and destruction, between energy release and energy absorption, creates a dynamic environment in which galaxies are constantly changing. Black holes regulate the growth of galaxies, keeping them from growing too quickly or too slowly. In this sense, black holes serve as cosmic stewards, ensuring that the delicate balance of a galaxy's life cycle is maintained. Their ability to regulate the rate of star formation ensures that galaxies do not become overcrowded with stars, depleting the gas and dust needed to sustain future generations. This role as cosmic gardeners is essential to the continued health and vitality of galaxies, ensuring that they evolve in a steady, predictable manner over billions of years. But the influence of black holes extends beyond the galaxies they inhabit. The energy and matter they release into space can travel across vast distances, shaping the environments of neighboring galaxies. When two galaxies collide, their supermassive black holes often merge, releasing an immense burst of energy in the form of gravitational waves. These ripples in spacetime, first detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, carry with them the memory of the black hole's merger. The study of these gravitational waves has opened up a new way of observing the universe, allowing us to probe the most extreme events in the cosmos and offering a glimpse into the inner workings of black holes themselves. The merging of black holes is not just a violent, destructive event. It is also a creative one. The merger of two supermassive black holes can result in the formation of an even larger black hole, whose gravitational pull can influence the surrounding galaxy in profound ways. As these larger black holes continue to grow, they alter the structure of the galaxy, shifting the orbits of stars and gas clouds, and even triggering new rounds of star formation. In this way, black holes act as cosmic sculptors, shaping the very structure of their host galaxies and influencing the course of their evolution. The process of black hole growth through mergers is a slow and steady one, with black holes consuming matter over billions of years. As they grow, they accumulate more mass and energy, feeding off the gas and dust that surrounds them. This growth is not uniform, however, and black holes can grow at different rates depending on the amount of matter available for accretion. In some cases, black holes may experience rapid bursts of growth, consuming large amounts of gas and energy in a short period of time. These bursts of activity, known as active galactic nuclei (AGNs), can outshine the entire galaxy, creating a region of intense radiation that can be detected across vast distances. Active galactic nuclei are some of the most energetic and fascinating regions in the universe. They are powered by the immense gravitational energy of the black hole, which is released as matter falls into the accretion disk. The energy from this process can heat up the surrounding gas to millions of degrees, causing it to emit X-rays, ultraviolet radiation, and other high-energy wavelengths. These emissions can be observed from great distances, allowing astronomers to study the behavior of black holes and the environments they shape. The study of AGNs has revealed important insights into the role of black holes in galaxy formation and evolution, as well as their influence on the broader cosmic landscape. While black holes are often associated with destruction, they also play a key role in the creation of the structures that make up the universe. The energy and matter they release into space help to seed the formation of new stars and galaxies. As black holes feed on the gas and dust surrounding them, they drive the processes that lead to the birth of new stars and the creation of new galaxies. This feedback loop between black holes and their host galaxies ensures that the cycle of cosmic creation and destruction continues, driving the ongoing evolution of the universe. In addition to their role in galaxy formation, black holes also help to shape the broader cosmic web, the vast, interconnected structure that spans the universe. The presence of supermassive black holes at the centers of galaxies helps to anchor them in place, influencing the motion of galaxies within clusters and ensuring that the cosmic web remains intact. The gravitational forces exerted by black holes also play a role in the formation of large-scale structures, such as galaxy clusters and superclusters, which are the building blocks of the universe's large-scale structure. As we continue to study black holes, we are only beginning to scratch the surface of their true significance in the universe. These enigmatic objects, once thought to be cosmic voids, are now understood to be essential players in the ongoing evolution of galaxies and the universe as a whole. Their role as cosmic gardeners, shaping the growth of galaxies and the creation of new stars, is a testament to the profound influence they have on the universe. By studying black holes, we gain a deeper understanding of the forces that shape the cosmos, and we begin to glimpse the true complexity and interconnectedness of the universe itself. The quiet work of these cosmic gardeners, nurturing and controlling the evolution of galaxies, is a reminder that even in the darkest corners of the cosmos, life continues to grow and flourish. As we approach the final piece of our exploration into black holes as cosmic gardeners, it becomes clear that their role in the universe is far more profound than merely consuming and dissipating matter. These enigmatic objects, once considered to be the ultimate destroyers in the cosmos, are in fact active participants in the creation and evolution of the universe. Their influence spans across time and space, shaping galaxies, stars, and the very fabric of the cosmos itself. One of the most fascinating aspects of black holes is their ability to regulate the growth of galaxies. Supermassive black holes, which sit at the center of most large galaxies, exert an incredible gravitational pull on the stars and gas that surround them. This gravitational influence extends far beyond the immediate vicinity of the black hole, shaping the overall structure of the galaxy. By regulating the rate of star formation, black holes ensure that galaxies do not grow too quickly or uncontrollably. The energy emitted by black holes, through processes such as accretion and the release of radiation, can heat up the surrounding gas, preventing it from collapsing into new stars. This feedback mechanism ensures that galaxies remain stable, with a steady flow of energy and matter. However, the influence of black holes is not just limited to regulation. These cosmic giants also play a critical role in the creation of new stars and galaxies. As a black hole pulls in matter, it can generate intense heat and pressure in the accretion disk, causing the surrounding gas to collapse and form new stars. This process, known as starburst activity, is one of the ways in which black holes contribute to the ongoing cycle of creation in the universe. The gas and dust that once made up the matter falling into the black hole is repurposed, transformed into new stars, planets, and other cosmic structures. The interaction between black holes and galaxies is a dynamic process, with the black hole acting as both a creator and a destroyer. In some cases, the energy released by a black hole's accretion disk can cause the surrounding gas to expand and disperse, stalling further star formation. In other cases, the same energy can trigger the collapse of nearby gas clouds, sparking the birth of new stars. This delicate balance between creation and destruction ensures that the evolution of galaxies remains in constant motion, with black holes playing a pivotal role in this cosmic dance. In the larger context of the universe, black holes act as a kind of cosmic recycler. The material that falls into them is not lost forever. It is transformed into new forms of energy and matter that contribute to the ongoing development of the cosmos. Even as black holes consume matter, they return energy to the universe in the form of radiation, creating a continual cycle of matter and energy that shapes the structure of galaxies. The idea that black holes can both consume and create reinforces the notion that the universe is a dynamic, ever-evolving system. But the role of black holes as cosmic gardeners goes beyond the galaxies they inhabit. These massive objects also contribute to the larger-scale structure of the universe itself. The gravitational pull of black holes influences the motion of entire galaxies, causing them to move through space in intricate patterns. When galaxies collide, their supermassive black holes often merge, releasing immense amounts of energy in the form of gravitational waves. These waves, first predicted by Albert Einstein and later detected by observatories like LIGO, carry the imprints of these cosmic collisions, providing a unique way of observing the universe's most extreme events. In this sense, black holes are not just isolated objects. They are integral components of the cosmic web, linking galaxies together and contributing to the structure of the universe. As scientists continue to study black holes, they are discovering more about the profound role these objects play in the cosmos. The observation of gravitational waves from black hole mergers, as well as the study of the energy emitted by black holes, is providing new insights into the nature of these objects. By observing how black holes interact with their surroundings, scientists are beginning to piece together a more complete picture of how galaxies, stars, and even space itself are shaped by these mysterious entities. One of the most groundbreaking discoveries in recent years has been the first-ever image of a black hole, captured by the Event Horizon Telescope in 2019. This historic image, showing the shadow of the supermassive black hole at the center of the galaxy M87, has provided a new way of studying black holes. For the first time, scientists were able to directly observe the region around a black hole's event horizon, offering valuable insights into the behavior of matter and light near these cosmic giants. This image is not just a scientific achievement. It is a testament to the ingenuity and perseverance of the scientific community in unraveling the mysteries of the universe. The discovery of the black hole at the center of M87 also reinforces the idea that black holes are not just passive objects, but active participants in the cosmic process. Their immense gravitational pull shapes the movement of stars, planets, and gas within galaxies, and their energy output influences the rate of star formation. By studying the dynamics of black holes, scientists are uncovering the intricate ways in which these objects contribute to the evolution of galaxies and the universe itself. Despite their crucial role in the cosmos, black holes remain some of the most mysterious objects in astronomy. We still do not fully understand how they form, how they grow, or what happens inside their event horizons. The study of black holes continues to be a source of fascination and excitement, as new discoveries challenge our understanding of physics and the nature of the universe. As we continue to study these cosmic gardeners, we are reminded that the universe is far more complex and interconnected than we can fully grasp, and that black holes, once thought to be destroyers of matter, are actually essential to the ongoing cycle of creation and evolution. In the grand scheme of things, black holes are the silent architects of the cosmos. They shape the structure of galaxies, regulate the flow of energy, and drive the birth of new stars. Far from being isolated and destructive forces, black holes are integral to the cosmic balance, playing a key role in the continuous dance of creation and destruction that defines the universe. As we continue to explore the mysteries of black holes, we will uncover even more about the delicate processes that govern the evolution of the universe, and we will come to understand that the cosmic garden, shaped by the quiet influence of black holes, is far more intricate and beautiful than we could ever have imagined.